Welcome to the fourth and final day of the meeting. Before we start, I just have two announcements. Ivette Fuentes will give her presentation at 12 local time today. That's a change. And the second one, Nelson Flores will give his presentation at 1:30 p.m. today. Okay, those are two. Okay, so we'll start today. It's a great pleasure to welcome Professor Kalidas Sen from the School of Chemistry, University of Hyderabad in India. And the topic is From Electron Density to Information Theoretical Measures to Structural Properties in Atoms and Molecules. Professor Sen, the microphone is yours.
Thank you. Good morning, everyone in Mexico, to all my friends and all other colleagues and friends of long time who are all online. I'm very grateful to the organizers, especially Professor Robin Pisagar, Humberto Laguna, and of course, my friend Rodolfo, whom I know for more than 3 decades. So let me begin my talk as the topic, as the title is given on already, From Electron Density to Information Theoretical Measures to Structural Properties in Atoms and Molecules. Now, over so many years that one has been working along with all the collaborators located at the various cities in the world. I'm most grateful and most thankful to them that I've been able to bring out 2 volumes, which are quite useful as the desk book for research scholars. And the first one is Statistical Complexity, about which yesterday there was a very nice review given by Professor Plastino. And of course, the confined atoms and molecules. And I have been, over these years, combining the 2 topics to do my research. So which is what I'm going to present here for the remaining period. So just next to where I sit, there is a immediate about 5 minutes walk, a building, which is C.R. Rao Institute. And Professor C.R. Rao, who is here, spends about 4 months every year until he was 92 years of age. And of course, unfortunately, he is no more with us. But it was a great pleasure to visit him almost every other day and discuss the various aspects. And the last time we met, we were discussing the measure for important things in natural science, such as diversity and also the texture. So this particular interest of mine continues, and let me hope that I'll be able to do something in the near future. And this is Constantinos Salis, who visited me about 8 or 9 years back. So we had a nice meeting in the office of Professor C.R. Rao. So that is such a fascinating thing, and I thought I will share with you. Then we have a large number of publications. The more recent publications, which are about 9 of them out of a total of 46. And I will be presenting only the first 35 or so, and the rest I will not be able to cover because that itself is a very daunting task, and let me see how far I succeed. But things like this list I have given so that whatever is not covered at all can be looked at by the students who are also part of this particular conference. So most recent work with my colleagues in Istanbul University, I have done something about complexity study of Q-deformed quantum harmonic oscillator, and with the friends from UK and US, David Thompson and Anderson, I have done something about Wigner crystallization. and so on. And 4 to 9 is the most recent, very active collaboration that I am associated with, along with the research group of Jayant Saha in Kolkata, Alia University, who actually presented some of the work. So I'm just giving for completeness sake the list that can be looked at leisure little later on. So the outline of presentation has 5 parts. The the topics here given are chosen to match with the title of the conference, which is about applications in natural sciences. So first application is Slater exchange parameter alpha, which is an exchange approximation to Hartree-Fock exchange given long time back in 1930 by Slater. And then subsequently it took various reformed names, finally the LDA of Cohen-Sham. Then the second one is mean excitation energy I for atoms, where there is a lot of interest in the experimental measurements of stopping power, which is related to mean ionization, mean excitation energy. And this work was initiated originally by Professor Vidin Schmidt's group, and both Robin Sagar and Rodolfo were part of it, which I will talk about. Then the third one, C, is Shannon information entropy sum for confined and shell confined atom. This work we did in 2005, and I'll talk about it. Finally, last two topics, shape complexity and stability of hydrogen molecular ion, and the scaling properties of information measure, with special emphasis on the shape complexity analysis of hydrogen atom in parallel electric and magnetic fields. So let me try. So first one is the Slater exchange parameter. So we started looking at the problem here using the Kullback-Leibler relative information entropy, which is given with reference to the Hartree density. So, and this was chosen the relative density with respect to the Hartree density was chosen because that happens to be the base of the density functionals that we have been developing since Cohen-Sham potential was proposed, the so-called evasive exchange correlation functional. So everything is starting with the ground level, as I will mention at the end of this particular section, that we have the very well-known Yakov ladder given by John Perdue, and it begins with the base. At the base of the ladder happens to be the Hartree model. So that is why the Hartree density was chosen. Now, the KLI measure without prime is with reference to the Hartree-Fock density, and therefore equation 1 defines the average discrimination in favor of Hartree-Fock density over the Hartree density. Now, the choice of Hartree density as a prior distribution in the denominator ensures that the focus is on the information content originating from the exchange interaction of the Hartree-Fock density. The second density in our focus, which we want to actually use in order to give a reasonable value based on the Kullback-Leibler relative entropy, is chosen to be the self-interaction corrected density, which is given here. This was originated by Whitehead and co-workers in Montreal. And there, the parameter alpha of the Slater exchange approximation is used in various ways. There can be a theoretical estimate depending upon the model that one uses for the exchange hole, or alpha can also be parameterized such that it reproduces the Hartree-Fock energy. So all kinds of values of alpha are known, but and this is the self-interaction correction. Our aim in this work is to find out the value of alpha, which makes the two distances, the relative entropy with respect to the Hartree density, with Hartree-Fock density here, and the distance of Hartree density with the self-interaction corrected exchange density that I just now mentioned in the previous transparency. Now, these two distances can be made to match or become very close. What we use is 10 to the power minus 5 of the integral values of KLI and KLI prime. And that is the choice of alpha based on the discrimination that we are talking about. So let's see what we get. So we get the values from lithium to argon, the theoretical values, calculating the density, the three densities. And these values of alpha actually make the distance KLI and KLI prime. There are two numbers of the integrals within 10 to the power minus 5. And these come out to be extremely close to the values of alpha, which are parameterized such that it reproduces the Hartree-Fock energy. So that was quite a nice, simple result. And we were very happy with the fact that the statistical distance measured by KLI is able to actually give us some very reliable answers. And then, of course, there are some possibilities of doing surprisal analysis and things like that for both the two KLI and KLI prime. And this is just the integrand, the log of density divided by the prior Hartree density. Hartree-Fock and SICLC can be done, and all this analysis can be done, but I will not be able to discuss those details. They are there in the publication. But then coming back to the Yakov ladder, at the base we have got these Hartree densities. And then we are now doing a similar analysis because we have a large number of exchange correlation functional and densities possible. So it will be nice to see what are the interactions active. For example, if a particular exchange correlation functional is including or having the characteristic of satisfying the so many fundamental or theoretical properties of the exchange correlation functional. Suppose some functional satisfies 5 of them, or some 10, some 15, and like. So we are trying to analyze very, very slowly, one by one, which one is contributing at what kind of surprisal analysis. So this is where the first part ends. I start with the second part, namely mean excitation energy. Now, this mean excitation energy is actually the work started by Professor Schmidt, Vedant Smith Jr., and then, of course, two of these, our friends from UAM are associated with that work. It's very nice work in 1998. So the stopping power can be defined in this expression, which is the loss of energy per unit of the width of the stopper. And the expression of mean excitation energy appears in the stopping power. This is an experimental quantity and therefore can be measured in solid state and also others. But then I, which is the mean excitation energy, is given by this particular equation, which is actually a weighted sum of the oscillator strengths of all excitations from ground state to any excited state n. All n's are included, which is a theoretical expression for this. However, it was shown in this particular paper, they used the local plasma approximation, where the plasma frequency is allowed to get modified due to the chemical environment of the scatterer or stopper, and there is a factor gamma that arises. But then that value for light atoms is supposed to be 1, and it varies from gamma varies from 1 to something like 2. Then we get finally the mean ionization energy I in terms of that gamma factor and the Shannon entropy in the position space of the atom and divided by the nuclear charge. So their result, the original result by Professor Schmidt and collaborators happened to be quite close. However, systematically, the experimental values of the mean ionization energies were larger than those obtained by numerical Hartree-Fock or even CI SD computations. So as one can see that instead of 50 for carbon, it is 81. So these are systematically larger. So we thought of looking at the Shannon entropy under the confined, spherically confined with impenetrable boundary, which satisfies the Dirichlet boundary condition, and see whether a particular radius of confinement of the sphere would lead to, or what are those radii of confinement which are reasonable, so that we get the values corresponding to the experimental results of the mean ionization energy. It turns out that in this work, we found that for hydrogen, the experimental value, because you have the confined density and therefore the Shannon entropy will be larger. And as a result, at about 3.794 radius of the spherical confinement, we get the experimental value, which is 14.469. And like that, we are able to rationalize the results, which are quite convincing in the sense that the sizes of the spherical radius are quite reasonable. Well, I must mention in this particular paper that we did, I did the acknowledgement to Professor Eugenio Lecu, and I sadly have to say that he is no more with us. But this is a conference that we attended, all of us, on 7 to 9 September 2011. Here is Eugenio, Norberto, Garza, and Salvador. So this is just a nice memory that I have. Incidentally, I first went to the UAM in 1995, thanks to Professor Gasquez, who was at that time the president of the university. And we met each other and interacted in Professor Bob Parr's lab in North Carolina, and he was able to invite me there, and I am very grateful to him. My host was in 1995, Professor Marcelo Galvan. And I have constantly kept in touch with all the friends and made more and more friends from UAM and, of course, UNAM. And I really appreciate that particular opportunity given to me, and I enjoy it very much. Now, the C part, Shannon entropy, information entropy sum for the confined atoms. Now, this particular this particular work was actually started because of the BBM bound that was given in terms of the total Shannon information entropy for a dimension D. And this is the original paper of Ivo and Jerzy Myslewski, and this paper was in 1975, and he did a similar information entropy uncertainty like result in 2006 after a long time. So this has actually resulted in catalyzing a lot of activity in the variety of the information measures, which this conference has been able to showcase all along. So this was the bound, and it's very interestingly, this bound given earlier was carrying a dimension part in it as the lower bound. So this is interesting. And for hydrogen atom, this particular result on the left hand side is the computed results using hydrogenic orbitals for the ground state. And of course, one is very nicely able to see that this is satisfying the lower bound given by 64343. Now, the idea was that can I sort of find some confined systems where this bound is not obeyed? And I hope that that could be a possibility. So we started doing this work. So I confined using the usual spherical confinement from 0 to R, which is the Dirichlet boundary condition, which is single cavity. This work was started long time ago by uh, people like Michels, Debord, and then of course Sommerfeld. And along with this particular single radius confinement from 0 to R, when the radius of confinement is infinity, it is a free atom. We at the same time around 2005, we generalized this model to include the shell confinement so that there are two radii and you can keep the outer radius fixed and the inner radius can be changed from 0 to all the way to the final radius, very close. Or you can keep the inner radius fixed and the outer radius can be compressed. You can also have a shell of 1 unit length going all across as you increase the inner radius from 1 to 2 to 3, so that every time the outer radius remains 1 plus 1, 2 plus 1, 3 plus 1, and like that. And so you can scan the different regions of space. So this is what I was talking about. You have inner radius, outer radius, and this is the model, this is the potential. The electron is confined in the white area. And so the one possibility is that you have vary the inner radius, keeping the outer radius fixed. So here, for example, outer radius is at 10 and inner radius is going from 1 to 2 to 3 up to 9 to 10. Then other possibility is that you always keep the R1 minus R2 as 1 and you change R1 inner radius as 1, 2, 3, 4, 5. So that outer radius is 2, 3, 4, 5. So that you have all over the space a shell of 1 atomic unit. It can be 2 atomic unit and so on, depends upon your interest. So, well, this is therefore taken as the system where we hope to get, because you confine the density becomes compact, and then we hope that this may lead to the total entropy in the position and momentum space as going below the lower bound. So to our very pleasant surprise, what we found was, well, this is the first calculation of confined atoms of hydrogen isoelectronic series, helium isoelectronic series, and lithium atom and boron atom. And we did single confinement as well as the shell confinement. For shell confinement, for excited state of hydrogen, we used the inner radius as R1 and outer radius was varying. So we wanted to see, this was perhaps the most, perhaps the stringent test of the BBM bound. So let's see what we got. What we got was for the hydrogen series, we in the ground state, we got the total Shannon entropy, sum of entropies, Shannon entropies in position and momentum space, changing with the radius of confinement, single radius of confinement. Each time we got one minimum. And it went on decreasing. We hope that it will go below the BBM bound, which is given here. But it just went up after we started confining more. So that was a very nice result. And we were able to get a minimum total Shannon entropy value for the ground state hydrogen-like as well as the ground state helium-like atoms. But for the atoms and isoelectronic series for number of electrons more than 2, where you have the K shell plus L shell, we don't get such nice single minima. You have maximum first and then a long tail of minima. So this is what we get for the this is the same result for helium series, but which has only K shell, similar to the hydrogen. And then we have for the lithium and boron, we did Kli functional here. For helium series, we did Bliff functional. And for hydrogen, the hydrogen atom that we know for the confined system. So all cases, we got minimum or combination of maximum minimum, which was very nice. And each time through all these very, very tough tests of the BBM bound, we found that the bound is always obeyed. And this was very nice. So, well, later on, we went on to do all the other information entropy measure, not just the Heisenberg, but the total Shannon, then PR, and the product of the Fisher and so on. Every time we have minimum. Then we did a dimensional analysis to get the scaling properties of these particular information entropic parameters, and we were able to get the isoelectronic Z dependence of the scaling. So I'll talk about it in our last example, little more detail. Now stability of hydrogen molecule ion. So here we use two measures of complexities. One is what was mentioned, which is the modified LMC complexity, which is having an exponential Shannon entropy, which satisfies the special property that Plastino talked about yesterday. And of course, the Fisher-Shannon plane, which is also a complexity measure, which we sort of were able to put together when I was participating in the research going on in Jesus Dejesa's lab in Granada. And Carlos is in the audience. He will remember our beautiful collaboration. And so let me just give the result. So this is the LMC complexity, shape complexity, where density is such that the measure of entropy is normalized to 1, and the density is normalized to 1, and we use that density to calculate the various information theoretical properties, defining the measure of or the distance from the equilibrium d, as well as the Shannon entropy exponential. So if you plot the two the position space and the momentum space complexities in that fashion, which is LMC complexity, we find that there is a minimum very close to the equilibrium distance of H2 plus. Similar result is obtained for Fisher-Shannon product, which is another measure of complexity. I will show you that these two measures of complexity as defined originally actually have the same scaling behavior with respect to the parameters of the potential. Now, this work, well, this is about the shell confined of the previous thing, but coming back to the hydrogen plus molecule, the more recent work by Asta Shakevich from Moscow State University in two papers in 17 and 19 have actually vindicated the findings. In the second paper, they have also included the excited electronic states of H2 plus. Now I come to the last part, and due to the time constraint, maybe I will have to rush through very quickly. So let me just begin here by introducing the scaling properties. Now, scaling properties are the properties which are obtained by looking at the Hamiltonian of the Schrodinger equation of the corresponding property and trying to sort of work out some way of reducing the Schrodinger equation in the form of the parameters of the potential, let's say S1, S2, S3, these are all scaling parameters, which are dimensionless. And the definition of scaling parameters which will tell us how the scaling actually is taking place with respect to the potential parameters or parameters in the potential part of the Hamiltonian. And the measures that we talk about is starting was HUP, Heisenberg uncertainty principle measure, or Shannon entropy sum, Fisher product, Onesescu product, Rayleigh entropy sum, Salis and Fisher-Shannon plane that I just now used, and the compressivity measure. So these are the information theoretical measure which we are going to work with. And what we do is, these are the various kind of potentials, the standard model model potentials of quantum mechanics, which we use, and we take where we derive these, we change this potential in terms of these parameters such that the Schrodinger equation corresponding to this becomes only dependent on the scaling parameters, which are dimensionless. For example, here S is for Poiseuille-Taylor potential, the S is H cross mu square root capital M and Z, and like that. For example, for truncated Coulomb or Morse potential, the S becomes this and this, dimensionless property. So we have to find that out. It is very simple exercise, but has got very, very good insights into what we are doing. So this is a work that I have picked up among various others, which I find is interesting because it uses a system where we use a composite information measure and in particular the shape complexity for hydrogenic atoms like Z is equal to 1, Z is equal to 2 for He plus, and we put them in parallel magnetic and electric fields. So, well, if there is no electric field, just in the presence of magnetic field, you have, we consider, let's say, 3p and 3d levels where the projection along the z-axis of the angular momentum is 0. So 3p 0 and 3d 0. So if the electric field is absent, then there are two good quantum numbers that are there, and therefore the two because of 3p0 and 3d0, the two symmetries are not the same when there is no electric field, as a result of which we will have the energy is going to all values, including the crossing. However, if we switch on the electric field, then the let's say in the z direction, the parallel direction that of the magnetic field, then the two symmetries become the same, because there's only one good quantum number, because the azimuthal quantum number is no more a good one. As a result, we are able to have what is very well known effect as the avoided crossing. So the energies go on. One of the energy, let's say 3p0, will go on increasing and then decreasing as we change the magnetic field at constant electric field. And the other one, namely 3d0, will come down and then go up, as we shall see very soon. So what we do is we are able to find out a large number of these information theoretical measure, and we are able to show that these two, one scaling factor which is dimensionless depends upon B, and it scales as Z square, and the other one, the corresponding electric field F scales as Z cube. Z square and Z cube. And this is this is a very nice simple result, and we will see how it actually plays out in the actual. I'll just go through quickly. So this is the Hamiltonian of the magnetic field and the electric field, and we change this R to R prime, where R prime is lambda times R. This lambda is chosen such that the value of potential energy of the transformed Schrodinger equation becomes 1 by r prime, and that fixes the value of lambda, and this lambda appears just as a parameter, and then two dimensionless parameters S1 and S2 just totally describe the transformed Hamiltonian in this form, and therefore we have the energy scaling for MZBF as 1, 1, S1, S2. And similarly, the wave function in the position space scaling like that, S1 and S2. And density will scale again in terms of S1 and S2. The momentum space analogously can be wave function, then density, and that is here. So we get the sum. Well, you can see that one is scaling as lambda 10 to the power -3, other is scaling as lambda to the power 3. So that if we take the product or sometimes sum, we will not get the lambda. But the fact to remember is that while let's go through the scaling property of the Heisenberg uncertainty principle. So again, the wave functions in the position and momentum space, the deviation can be written down in terms of lambda and a function which is only dependent on S1 and S2, and therefore similarly the variance of the momentum space can be written down as lambda inverse this, so that if you multiply the two, whereas the individual spreads of the position space and momentum space can have any value, because the Z gives you the strength of the field. Originally, Z is related to Z, the lambda is related to Z. But if you take the product of that, the lambda, it is free of the strength of the field, so that you just get H cross, and everything is now dependent on S1 and S2. And this is uniformly the case for all the other parts. For example, the positional space Shannon entropy and momentum space Shannon entropy have this right-hand side, so that if you add, this part cancels out and you have only the sum. So therefore, it is whereas individual entropies in position and momentum space can have any arbitrary value, their sum is constrained and bounded from below by the BBM bound. And similarly, the product, you can see it goes as lambda square in the position space. In the momentum space, it goes as this is lambda 1 by lambda square, and this is lambda square, so that the product is free of the strength, and so on and so forth. These are all very simple examples that we can continue. And similarly, the Ionescu, that is the disequilibrium or the distance from equilibrium in both the spaces, has similar feature. Renai sum has again the scaling of alpha and with R and P. This is the total R, alpha R and P, and the total thing, which is given as the sum. And then we have Salis entropy ratio. Again, the same thing. We can always have the ratio of P and R as dependent only on the S1 and S2. So this is the final one. Of course, this is Fisher-Shannon measure, the other complexity measure, and I'll be showing the results only for the shape complexity, which is the LMC complexity in this particular form, exponential times the disequilibrium. And we have the two possibilities of position space and momentum space of the shape complexity. And notice that the in the given space, either position or momentum, the scaling is the same. And so is the case for the Fisher-Shannon plane. That is another measure of complexity. And they have the similar scaling, like the R space Fisher-Shannon product plane and R space LMC product plane has the same scaling behavior. So therefore, and Salis is again analogously can be written down the same way. The results are here given, and that is something that is very, very interesting. So this is the avoided crossing. So we have two levels, 3P0 and 3D0, and this is when you have magnetic field varying on this axis, and the ionization energy for each state related to the ground state is plotted, and there is because of the similar symmetry, there is a as the at the fixed electric field is fixed here. We are varying magnetic field in this particular way because the minimum appears to be between this range of external magnetic field when the parallel electric field is kept fixed. So we keep electric field fixed and magnetic field is being varied. Now this is for nuclear charge as 1, which is a hydrogen atom, and this is corresponding to nuclear charge 2 for helium plus ion. Now we have a lot of these the possibilities. One simple one is that when Z is 2, then the scaling is such that if the electric field here is 1.946 10 to the power minus 6, the electric field that is necessary here to have the similar kind of topological behavior for the avoided crossing is the Z to the power 3, because that is the scaling for electric field, and for magnetic field the scaling is Z to the power 2. So therefore, if you multiply the magnetic field here by 4, you get this magnetic field. Remember, here is 10 to the minus 2. There is no 10 to, it is directly in atomic units. And if you have the electric field here, multiply this by 8, you get this particular electric field. So this is what we are going to do now, having pointed out. So there is a position where there's a minimum distance. This is not as wide as this one, but the topological features are the same. Now we go to the shape complexity, and which is what is of interest. How does the shape complexity show its sensitivity to this behavior of avoided crossing? So this is the general point of the general behavior of the shape complexity. If you plot shape complexity as a function of external magnetic field at a fixed electric field, which is a parallel field, then you have got the features that the 3D part, both the shape complexity have a double hump structure, and there are topological features which can be counted as the one where the two shape complexity become equal, which is the midpoint of the two minimum of the humps. So that is first point, and that will be called as a critical magnetic field, where the two complexities become the same. The two shape complexities are same. Then there are two minima of the 3D and the 3P, which are shifted left and right from the center of the critical magnetic field. You also have the first hump of the 3D having the same height as the second hump of 3P0. Similarly, the first hump. Similarly, this is same as that XX, and then the first hump here of the 3P has the same value as the second hump of 3D. So this value is the same, and then of course there is a crossing point. All these things can be computed, and we find that at a fixed value of 1.946 of the electric field, where the magnetic field is varied, for Z is equal to 1, the curve is like this. Topologically, the complexities have to remain the same because this and this are related via the Z scaling. So that this has been chosen so that S1 and S2 pair will give from here to here the same value of the shape complexity. So this is same. However, yes, thank you. I'll finish in time. So this and these values are different because of the scaling, and one can simply obtain the same kind of scaling of magnetic field 4 times for the Z is equal to 2, and 8 times for Z is equal to 2. You will get the same particular parameter. By the way, every topological feature, including its location at the complexity values can be expressed quantitatively using the scaling relationships, which is given by this particular result. So this is therefore interesting, and one can go on doing many such analysis. The importance of such an analysis that, look, if we know the avoided crossing and the shape complexity features for one member of the isoelectron series, using the scaling rules, you can predict the similar properties for all the other members of the isoelectronic series. So shape complexity seems to be a very, very nice and sensitive parameter, which gives a very nice topological double hump structure as a function of the magnetic field at constant electric field. Now, there was this important paper that we did together with Elvira Romera and Agnes Nagy. We generalized the relative complexity measure, which is given in this paper, using the this was trying to consider the decay model, which Elvira talked about is on the second day. So I have to thank a large number of persons who have actually influenced me, who have taught me things, and I continue to interact with them. And there's a large list, but if I have left out some, my apologies. But then let me read out Montgomery from Kansas, Jacob Catriel from Haifa, Norberto Aquino, Rodolfo Ezequiel, Jorge Garza from Mexico, UAM, then then we have Carlos, JC, Carlos, and Rosario, who was part of that work of the magnetic and electric fields. She was an expert in that kind of analysis. Then Dr. Vinod Prasad, who will be speaking later today, Agnes Nagy, who has been one of the most guiding spirit for my work, starting from density functional days. Richard Hall from Montreal, Concordia, who is unfortunately no more. Vladimir Pupisho from Moscow State University, who is no more. Then, of course, Jesus, David Thompson. These are my friends from Greece, Thessaloniki, and one of the collaborators, Mustas case, is going to, I think he's part of this conference. Then Alex Borgo and Paul Gerling from Brussels, Professor Patil from IIT Bombay, Jayan Saha, Amlan Roy from Ayers, Kolkata, and I think I forgot Alberto Vela. I must mention him. And of course, I mentioned earlier on Marcelo Galvan and Professor Gasquez. So thank you very much.
Thank you, Professor Sen, for your very interesting talk. Keeping in line with the theme of the meeting, which is uncertainties, we have some further changes to announce. Ivette Fuentes, her talk will be at 12 today. Paul Ayers will be speaking at 1:30, and in the afternoon session, Nelson Flores and Robin Segar, they are interchanged. Okay. Thank you. See, okay, so is Barnali connected?
Yes, Professor.
Yes.
Can you hear me?
Yes, we can, Barnali. Please, yes. Could you share your screen so we can?
Yes, let me try. It's not sharing.
here. Share screen.
Yes.
Yeah, you can pause here. Let me see this.
again. And the next speaker is Professor Barnali Chakrabarti from the Department of Physics, Presidency University in Kolkata in India. And the title of her talk will be Unbounded Entropy Production for Repulsive-to-Attractive Interaction Quench in Long-Range Interacting Systems. Barnali, please go ahead.
Okay, thank you, Professor. Good morning, everybody. Greetings from Sao Paulo, Brazil. Well, it is an exciting opportunity for me to present my work in these wonderful occasions of commemorating 50th anniversary of UAM. So I am thankful to the organizer for giving me the opportunity to present my work here. In the last few days, we have seen many interesting discussions, presentations on how the concept of information theory has raised its application in diverse disciplines of science, ranging from physics, chemistry, statistics, computer science, and many more. My research area is quantum many-body physics, more precisely ultra-cold atoms and molecules in the strongly interacting limit. So today I am going to present one of my research work, which basically exhibits some exotic dynamics in the 1D quantum gas having long-range interaction. And there is some unseen phenomena when you quench the system from strongly repulsive to strongly attractive regime. Now, as this is very hardcore part of my personal research, so I believe that before presenting my work, let me give a brief preamble that how the concept of information, quantum information, has been cultivated in the research platform of ultra-cold quantum gas. We all know that since the first experimental realizations of ultra-cold quantum gas and Bose-Einstein condensation in the year of 1995, there is a revolution both in the theoretical research and the experimental research. We know that there are the three key advantages with these ultra-cold platforms. The first one, that ultra-cold quantum gas exhibits unprecedented amount of experimental control. The quantum gas can be isolated completely from its environment, and at the same time it exhibits novel control entanglement creation. These three key features of the ultra-cool quantum gases has made a complementary platform for understanding the condensed matter physics and the solid state physics. And since 1995 till today, if you follow the research papers published in the Nature, Science, Physical Review A, Physical Review Later, you can see that it is basically an interdisciplinary research area when the concept of condensed matter physics, atomic molecular physics, statistical physics has merged together. And in the recent days, we find that the most common review
Okay, we had some technical problems. We apologize for that, and we will have to wait until Barnali can connect again.
I can open.
Okay, you're.
Is it okay now?
Yeah, Barnali. Yes. Yeah.
I don't know. Maybe this is the problem of university internet connections. It falls suddenly.
Yeah, we think so.
Okay.
One option. Barnali, no, it's okay. Yeah. Okay. So if you can just resume, maybe we will have better luck this time.
Yes. Okay. So these
But-
dipolar systems.
Sorry, Barnali.
Yes. Yes.
Your screen isn't being shared. So could you please share the screen?
It's not sharing.
No, it's not sharing. No.
Let's go back there to the browser. Share. Allow. Select beauty, display, and then share. Now it's everything okay.
Good. We have your screen, Barnali.
Yes.
So
So I was trying to mention that these long-range dipole-dipole systems, the dipolar molecules are the unique members in the platform of quantum informations and quantum technology, because they exhibit some exotic quantum phases like quantum droplets, like supersolid phases. They also exhibit some metastable states having long lifetime and robust entanglement. Okay, so maybe I choose the options of the slides. So yes, so at the same time, the long-range interacting systems are the prime member to understand the out of equilibrium dynamics. Out of equilibrium dynamics means you prepare your systems in some initial state with some definite parameters like interaction strength, the nature of the interactions, and then suddenly or adiabatically you quench one parameters of your Hamiltonian. That is the quench protocol. And these out of equilibrium dynamics have seen rapid experimental progress to understand the quantum coherent features in the far equilibrium scenario. The most important point is this exponent alpha can be engineered in the experiments by controlling and manipulating atomic, molecular, and optical systems. However, theoretically, it is a challenge because the scarcity of the appropriate many-body calculations, the existing theoretical calculations like mean field theory or the mean field theory with some additional corrections are not appropriate to address such highly correlated and entangled systems. They are unable to capture the complex non-equilibrium phenomena. My research group has been tried to address these strongly correlated ultra-cold systems by introducing some ab initio many-body formalisms. We call it multi-configurational time-dependent Hartree or MCDTH. X means extends for bosons or extends for fermions. The MCDDH was initially developed by the group of Professor Lorenz Söderblom in Heidelberg. And here I address two seminal papers. One is PRL 99 and another is PRL 77, which basically demonstrate that how the mean field theory is pushed to best mean field theory and then pushed to multi-configurational time-dependent Hartree. In last couple of years, my research group is engaged to address these highly correlated out of equilibrium dynamical features by appropriately introducing MCDTHX. Here I just give few of our recent research publications where we address different features of non-equilibrium phenomena. But the most important thing, what we observed, that these kinds of the strongly correlated systems cannot be described by the traditional definitions of the information's entropy. We need to introduce some new variant of the many-body information's entropy, which can appropriately take care of many-body correlations. Now, my today's talk is mainly focused on this paper, which I have published in New Journal of Physics, 26th volume. It is published in 2024. Okay, but before introducing results and the quench protocols of my system, let me very briefly overview the multi-configurational time-dependent Hartree. You can see the Hamiltonian, where you have n number of the interacting particles. It may be collections of bosons, it may be collection of fermions. On the right-hand side, you have two terms. One is the one-body term, small h hat. It takes care of the kinetic energy as well as the external trapping potential, which goes as the one-body term in the Hamiltonian. These trap potentials may be some kinds of the harmonic trap. It may be some optical lattice. It may be some combinations of harmonic potentials, optical lattice, or whatever you can have just to reproduce the corresponding experimental scenario. The second term on the right-hand side is the two-body interaction term. This interaction term you can choose as a contact interactions or long-range interactions. And theta t, it is a time-dependent weight function, which basically handles the quench process. So we try to solve h hat psi is equal to ideal psi del t. Now the traditional answer for the many-body wave functions is the time-dependent Groth-Spitavetsky, TDGP, where you can see that the total many-body wave function is decomposed in the product of single particle states, phi r1, phi r2, phi rn. So there is no correlations between the two atoms. So this time-dependent Groth-Spitavetsky is absolutely okay when you have condensate. That means you know that all particles of your system, they occupy the same single particle state. But when we talk about the experiments, in the experiments, by utilizing the phase-back resonance, you can do whatever you like. You can choose, you can make a very strong interaction. You can have very strong repulsive as well as attractive interactions. You can have highly correlated systems. So you are far above of these condensates when the number of the particles are distributed in many orbitals. So we call it as the fragmented state of the quantum many-body systems. So MCDTHX propose these kinds of the answers, which is the summations of CNT and bracket NT. So there are the two time-dependent parts. You can see my cursor. This CNT, it is the time-dependent coefficients, and the permanent is the arrangements of the number of the particles in different orbitals. So basically, these kinds of the many-body answers can take care of the transitions between condensations and fragmentations. I am not going in details because in the background, it has lots of theories. It is discussed in those research papers I mentioned that was developed by Ophir and Alex Telskopf in Heidelberg. Just briefly summarize that you will have a couple set of equations of motions. One is in coefficient, another is in the permanent. And both are variationally optimized with respect to the all parameters at any time. Fine. Now, theoretically, we can claim that when you have infinite number of the orbitals, then this permanent spans the complete Hilbert space. So the expansion is exact. So the MCDTHX answers it is exact by its constructions. But when we do some numerical simulations, we reduce the number of the orbitals as per our requirement. We limit the size of our computations according to our workstations or clusters available. So what we do the simulations with increasing number of the orbitals, and we look for the convergence when the last orbital populations becomes insignificant. And we also observe that the different dynamical observables, they converge. So we can claim that MCDTHX gives us numerically exact results. And also it is worth mentioning that as we have the time dependence, both in coefficient, if I go to my earlier slide, as the coefficients and the permanents both have the time dependence, unlike the case of the exact diagonalization, when you have the fixed time independent orbitals, we have the time dependence in both cases. So it is ideally suited when you try to understand the inbuilt correlations in the dynamical evolutions. That means when you quench your systems and let the systems to evolve dynamically, so you have to follow the dynamical correlations. That is possible in the platforms of multi-configurational time-dependent heart rate and not possible when you have the fixed orbital and such. Okay. Here I want to mention that when we try to utilize this multi-configurational time-dependent heart rate, we observe that the traditional definitions of the Shannon information's entropy is insufficient. We tried to follow the work of Massen and Panos. They have also some works for the systems of fermions and interacting bosons. The one-body information's entropy defined in this way can take care of only the one-body term rho xt and rho kt. So SIE takes care of the localizations and delocalizations in the conjugate space. But when you have the highly correlated many-body systems, this SXT and SKT becomes insensitive. I give few of our references. It is little bit old, but one can follow that how we have demonstrated that the insufficiency of this one-body information's entropy and how we have developed the concept of many-body information's entropy. Now I quickly review the way we define the different variant of the information's entropy. Okay, so according to my MCDTHX answers, I have the time dependence in coefficient, I have the time dependence in the orbitals. Now equation 1, 2, and 3, that is the coefficient Shannon information's inverse participation ratio, that is almost known to us because we utilize coefficient inverse participation ratio to understand the chaotic systems, and n-body coefficient entropy. These are defined in different way, but what CNT signifies? It signifies that during this time evolutions, how these coefficients dynamically distributed in the Hilbert space. So when initially, if your pre-quench state is quantum coherent state, so obviously the contributing coefficients will be smaller. With time, When the system evolves, this information's entropy will increases because C and T will increase dynamically. And if your system relaxes at some long time, then this information's entropy will saturate. But please note that when you do the Gross-Pitafevsky mean field theory, you have a single coefficient. So equation number 1 and equation number 3 will have 0 trivially because you have the logarithmic of the coefficient. But in the MCDT-HX answers, this coefficient is not unique. It's not absolutely invariant because you can arrange the permanence and coefficients in the other way. So we also define occupational Shannon information entropy, which basically depends on NIT. NIT means how the orbitals have the time dependence during the time evolutions. So it can follow the dynamical fragmentations during the dynamical evolutions in your out of equilibrium dynamics. And again, it is point to note that for the mean field theory, as you have only one orbital, S and T is 0 trivially. So they have no meaning in the platform of mean field theory. Now I enter to my recent observations, where we like to present some exotic and fascinating dynamics of one-dimensional quantum gas. And this quantum gas may be fermions or maybe bosons, but we concentrate on the long-range interactions, which can be given by this expression GD divided by x to the power alpha plus some cutoff epsilon. This alpha can be tuned experimentally, and also we tune alpha in our theoretical simulation. GD is the strength of the long-range interaction. So what is my prequench state? At t less than 0, we prepare my state of 5 strongly repulsive atoms. It may be bosons or it may be fermions in the harmonic trap, and the interaction strength is GD is very high. In the MCDT-8X unit, GD is equal to 100. Now, what do you mean by the GD is equal to 100? We know that strongly repulsive regime is the TG limit, that is the Tonks gas. In the Tonks TG limit, when you have the bosons, due to this strong repulsion, these bosons escape their spatial overlap and acquire fermionic properties. In 2004, a seminal paper, this was the pioneering observations of the experimental observations of the TG gas. But in 2009 experiments, it was the experiments of Heller group. They also exhibit that not only very repulsive Bose gas, you can also create strongly attractive Bose gas. That is known as the super Tong gas. We may be confused that when you have very strong attractions, you may have some clusters. But no, it is not the fact. The super Tong gas, it is a highly excited, highly correlated gas-like state. It is a metastable state. That was the experimental observations, experimental demonstrations. But very little known about these STD transitions, again due to the scarcity of appropriate correlated many-body technique. So particularly in this work, we try to address some quench process when you have some systems of long-range atoms and you do the quench from very strong GD positive to GD negative. So you have TG to STG quench. The post-quench state is a super Tong gas and pre-quench state is a Tong gas. What is our results? Okay. Now to understand these dynamical properties of the long-range systems, let me see what we expect. What is our expectations? The non-equilibrium dynamics for the short-range interactions, it is almost established. It is known. And we know that the non-equilibrium dynamics for the short-range interacting systems, the system exhibits complete relaxation process, and it exhibits one single time scale. But there is few benchmark experiments, and this is the first experiment, New Journal of Physics in 2013. This was the first experiments with the spin chain problems, where this alpha exponent was dynamically tuned in these experiments, and they measured the two-body correlations. And in the JIG, that is the IJ spin-spin correlations, and they observed that the spin chain, they demonstrate two time scale. In long time scale, when you have far of equilibrium, then you have the complete thermalized state. But at some intermediate time, they observe some quasi-stationary states, which is the pre-thermalized states. That means the system stays in this quasi-stationary state. It's the metastable states. But not much theoretical understandings is done beyond this. So our research work is aiming to probe what is the underlying microscopic dynamics, what is the time scale of this equilibrium dynamics, how this relaxation process happens, and how to characterize this exotic supertom phase from the many-body perspective. Here is my results. Okay, so DDT less than 0, I have 100, which goes to TG regime. At T more than 0, that means we make the sudden quench process. GD is quenched from plus 100 to minus 100. I have alpha, it is equal to 3.0. But we have the similar features for the other values of alpha. I am just presenting one result. What does it mean? You can see there are 4 pictures because we have done the computations with m equal to 5 orbitals, then 10 orbitals, then 15 orbitals, then 20 orbitals. What we can expect? If you have a regular dynamics, if you do your simulations with gradual increasing in the orbital numbers, then gradually it will lead to some convergence phenomenon. But here we observe some irregular dynamics. For all cases of M, it doesn't matter. But for all cases of M, you can see near the time t it is equal to 0.5. For every case, there is a transition from chaotic scenario. What does it mean? It means that whether you have 5 orbitals or whether you have 20 orbitals, it doesn't matter. At the transition point, when the quantum gas collapses due to the strong attractive quench, all the number of the orbitals utilized in the computations are immediately occupied by this gas. So this is a typical pictures of classical gas. So this is not fragmentation. This is a violent fragmentations. If you have a supercomputer, if you can do the simulations with 30 orbitals, you will get the same scenario. So this is a transitions from quantum to classical gas. So the supertom gas has some classical gaseous behavior, which was also manifested by the experiment of the Heller group. And from the many-body perspective, we observe that this is related with the violent fragmentations during the collapse. You will get the same feature when you plot the coefficients. For the same quench protocol, here we plot the Ci square as the functions of the configurations, and the configurations in the Hilbert space gradually increases from 120 to 2000 to 12,000 to 40,000, because you are simulating with m equal to 5, 10, 15, and 20 orbitals. You can see nicely that for all cases, the coefficients occupies all the Hilbert space. The complete Fock space is occupied by these coefficients. So this is the typical characteristics of the classical gas. And this is the many-body manifestations of this supertom gas, which is a metastable gas. Now, this is the 2 pictures which we obtained from the time-dependent solutions of the many-body Schrodinger equations. Now, of course, we are curious to find out that what will happen to the entropy productions. You see, I am maintaining the same quench protocol. I demonstrate all the 4 measurements, 4 variants of the information's entropy, which I discussed before. In all cases, you can see that all the information's entropies, they start from a lower value because you have a highly coherent quantum gas in the TG limit, your pre-quench state, then it increases and then it saturates. So the saturations of the information's entropy tells you that the system relaxes. But the entropy production is not bounded. It depends on the number of the orbitals, 5, 10, 15, 20. It is gradually go on increasing. In the other kinds of the simulations which we have already done for the regular systems, we always found that a relaxed state is always associated with some bounded entropy productions. But these kinds of the exotic dynamics associated with the violent fragmentations, violent delocalizations is also associated with the unbounded entropy productions. Now, I like to give a very brief estimate of the saturations values. What does it mean? Or is it just the results of my MCDTHB? No, it's not like that. Let me take the help of the random matrix theory. It says that I am not the expert in this field. I have very limited knowledge, and I just took the essential parts of this random matrix theory, which I need to calculate the saturation values for my calculations. Random matrix theory says that for a time reversal symmetry and for d by d dimensions of the random matrices, the Gaussian orthogonal ensembles GOE has these predictions. These are the analytic expressions of SC, IC, and SN. We do not have any counterpart of SNC. So I can compare only these 3 variants of this information's entropy. And D is nothing but the configurations of my MCDT-HX with basically these. So you are distributing n number of the interacting particles in the m number of the orbitals. So you can calculate the number of the configurations of your Hilbert's case from these expressions. I just give one result that if you choose m equal to 15 orbitals, then these configurations will be close to 12,000, 11,600. And if you appropriately put on these values, these are the GOE estimates, SC, SN, and IC, whereas the saturations values in the earlier presentations, in the earlier transcripts, you have seen that that this SC, SN, and IC, they saturates. And if you carefully look at the saturations values, the MCDT-HB results are like this. They approach the GOE values, but GOE estimate is strictly valid when you have infinite interactions. In our simulations, we have very strong repulsions, but it is never infinite, it is finite. But this is to be noted that there is benchmark agreement for all cases, for all orbitals, that occupational entropy, the orbital occupational entropy is in MCDT-HB has benchmark agreement with the GOE results. Okay, now my list, the rest of the part of my presentations basically try to understand the relaxation process for bosons and fermions. So this is again the representations of the 4 informations entropies. For a specific case of alpha equal to 0.7, we divide the 2 cases. You have one-dimensional system. So when alpha is less than 1, you have truly long-range interactions. When alpha is more than 1, you are close to short-range interactions. So when you have truly long-range interactions and maintaining the same protocol, GD goes from plus 100 to minus 100, you can see that SC, IC, and SCN have some kinds of complex initial dynamics. There are some kinks, but we are unable to probe the meaning of these kinks. Maybe there is some quasi-stationary states of a very, very small lifetime which we are unable to probe. So from this, we cannot conclude that whether any pre-thermal state exists or not. We can conclude that occupational entropy has a very smooth behavior and it approaches to GOE value and exhibits complete relaxation process at the time T is equal to 0.6. For a little bit longer interactions, when alpha it is equal to 2.7, the complexity in the initial part, it reduced, but again, we do not find out any pre-thermal phase. We get the pure relaxations here, 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 and the relaxation happens almost at the same time. T is equal to little bit larger here, but not much. It is better if we plot the separations between the relaxed state and the non-relaxed state in some kinds of the phase diagram. It's not a phase diagram. It is basically, we take occupational entropy as the order parameter, that is the matrix. And we have the alpha values because in our entire simulations, we simulate alpha from 0.5 to 4.0. And you can see this yellow part. This yellow part corresponds to highly correlated pre-quench quantum gas. And there is an exponential boundary. And you have this part where you have the relaxed state, which is the classical super top gas. If you do the simulations, maintaining the same protocol for the fermions, the complexity is huge. There are many kings, but Sn of T, it exhibits smooth relaxation process compared close to the time T is equal to 0.6. So Sn is a good candidate to understand this relaxation process. When you have much longer interaction, much hotter interactions, alpha it is equal to 2.7. Just like the bosonic dynamics, you can see that the complexity is reduced. All these informations entropy exhibit smooth relaxation process, and also Sn has the saturation value close to the GOE predictions, and the relaxation happens is close to T equal to 0.6. The corresponding phase diagram in the alpha T plane, if we plot this occupational entropy as the parameters, you can also observe a similar kind of exponential boundary. It is a little bit shifted on the right side for the fermions, but more or less the qualitative features, the exponential boundary remains same. So from here we conclude that the relaxation process for long-range interacting bosons and interacting fermions are identical. So this dynamics is universal. And here I like to mention that for the simulations, we have considered the spin polarized fermions. That means we didn't consider the spin half fermions. It's the spin polarized fermions. Now, this is the last results where I quickly overview that is it possible to control this relaxation process? Because when we look for the quantum information processing, which is the building block of quantum computations, we always look for the highly entangled state and the metastable state, the pre-thermal kind of the states, which has some longer lifetime. So here we have presented the information entropy for different kinds of the quench protocol. GD it is equal to 100 to minus 100. It is the thing which we have already discussed. But next we like to decrease the attractive interactions, minus 80, minus 50, minus 30, and minus 10. Now pay attention in the figure B because this has more regular behavior. You can see that this blue graph corresponds to very strong repulsive to very strong attractive, where there is no kinds of plateau. So no pre-thermal state is possible, only relaxations and exhibiting one single time scale. But gradually reducing the value of GD, you can see that the slope becomes slower. And when you have the quench from GD, it is equal to 100 to minus 10, this the lowest graph, you can see that it has some slower ramp initially, and then it linearly increases. What does it mean, this slower ramp? Slower ramp means with appropriate control of these GD interactions. Maybe we can start from not from so high interactions. Maybe we can control the initial GD and the final GD. Then some kinds of the plateau regions is appearing in the region 1, which signifies the possibility of attending some thermal states and also controlling the linear increase in the regime 2. You can see regime 3, there is no relaxations. So we conclude that control of relaxation process is possible. At least theoretically, we can simulate that. I'm not going to discuss anymore. So just let me conclude what we have observed. So in these non-equilibrium dynamics, we have proved the fascinating and very irregular dynamics of 1D gas, quantum gas, with the long-range interactions, which goes as 1 divided by r to the power alpha. It should be 1 divided by x to the power alpha, because we are considering the 1D Bose gas. And this alpha has been tuned. We observe some exotic features, some unseen features during this TG to STG quench. And this exotic dynamics is supported by the observations of violent fragmentations and chaotic delocalizations. We have also observed that this irregular dynamics is associated with the unbounded entropy productions. In the different many-body informations entropies, we have seen this. We tried to establish our results in a phase diagram where we have some kinds of the exponential boundary between the quantum gas, which is highly coherent, and the chaotic classical gas, which is highly incoherent. We have established the universality between the bosons and the spinless fermions. We tried to establish some appropriate quench protocol, which is the weaker quench protocol, such that you can appropriately control the relaxation process, and you can, we tried to give some idea for the future experiments, that how to obtain these interactions quench protocols in the experimental platforms. I'm sure that these kinds of the relaxation process, which we have simulated through MCDTHX, can be engineered in the near future in the platforms of trapped ions, Rydberg atoms, dipolar molecules, where long-range interaction exponent alpha can be tuned at per will. Okay, so I stop my presentations here, and this is a list of research collaborators with whom I'm working. They have enormous contributions to develop and implementations of the multi-configurational time-dependent heart rate. Not only the theoretical development, but it is also challenging the numerical implementations of MCDTHX code. So this is a short list of my research collaborators. Okay, so I stop here. Thank you for your attentions. And this is my email address where I am available for any kinds of further discussions or for any query. Thank you so much.
Professor Chakrabarti, thank you very much for your presentation. I would just like to remind the audience that any questions can be directed to the chat in Zoom, YouTube, or the WhatsApp. Okay. Thank you, Barnali.
Thank you so much.
Professor Roy, is Professor Roy in Zoom?
Yes. Good morning.
Wonderful. Yeah, we can hear you. And if you could just
Okay, very good.
if you could just share your screen just to make sure that we can.
Yes, I'm doing that. Is it visible now?
It is visible. That is great. Wonderful.
And audio is also okay.
Yeah, so just a couple of minutes, so we will go live, and then I will introduce you.
Thank you.
Sí. Mm-hmm. Okay, we're back again with the next talk. The next talk will be Professor Amlan Roy, Department of Chemical Sciences from EESER. I think that's the Indian Institutes of Science, Education and Research in Kolkata, India. And his talk will be Information Entropy of Spherically Confined Harmonium Atom within Density Function Formalism. Professor Roy, please go ahead.
Hello, good morning. Thank you so much for the kind introduction. And good morning or good afternoon or good evening, depending on wherever you are. So first of all, I'd like to thank the organizers, in particular Professor Laguna and his team, and giving me this wonderful opportunity to share some of our works in this prestigious conference. So this 50th year of commemorating the anniversary of UAM is a very big event, and I think that is a testimony to that important contributions that university has made in the Mexico and in the global scenario. And the topic is also highly interesting. Before I say anything, I am also very happy to say that in this particular topic, I was introduced by none other than Professor Kalidas Sen, who has already given his talk about 20 years ago. So I am immensely grateful to him. And also another of the speakers is also from my lab, Dr. Neetik Mukherjee. He is also going to share his works in this conference. So before we go to that, I would like to say one thing about our institute, which is Indian Institute of Science, Education and Research, Kolkata. So this is a chain of institutes which opened in the year of 2006. And this Kolkata was one of the very first institutes. And now currently we have 9 such institutes throughout the country. And the primary aim is to do basic sciences. So we have physics, chemistry, mathematics, biology, earth science, and data science recently. So the title of my talk is Information Entropy of Spherically Confined Harmonium Atom within Density Functional Theorem. So before I go to the main talk, I would like to say some of our developments or current activity, which is in our lab. So this is a density functional theory code, which has been developed in our laboratory over the last 10 years. It's not a very big thing, but it is called INDFT, and this slide shows some of the things which have been able to do and some of the things which remain to be done, and we are interested. So one such thing also is that quantum confinement in atoms and molecules, which we are working, but I'll still not present results from this work because these are unpublished works and it is work in progress. So we have done some response properties, we have done some excitation energy calculations, we have done some optimal tuning calculations, and also some TDDFT calculations we have done within this INDFT method. So, of course, a lot of things remains to be done. So we are currently working on that. So now I go to the title, the theme of this talk. So one particular confinement we are going to, we are interested to present in this is the harmonic confinement. And we have done works on the hard confinement and the shell confinement, some other stuffs, and those results are published, and I'm not going to share those results. So in particular, we are going to discuss the quantum dot and 2 such methods which have been developed in our lab. I will mainly focus on that. And some results on the quantum information entropies will be presented. And I'll conclude with a few things in this. So the various talks have already provided a platform for this confinement. The main idea is that the sizes we are talking here should be on the atomic scale, and we know that it should be incommensurate with the de Broglie wavelength, and in such domain, very interesting electrical and optical properties can take place, and they are substantially different from their free counterparts. So we should be mainly focusing on that. And here is a cartoon from the famous paper by Roald Hoffmann and Rochella showing the landscape of the high pressure chemistry in particular, starting from 0.01 gigapascal to 1 pascal, and then 10, and then various chemical phenomena occurring at various pressures regions. So, and these are some of the experimental evidences which I have gathered from various papers. So we can, confinement can be of various types. We can have cylindrical confinement, we can have spherical confinement, we can have also atoms encapsulated in various cages, in particular the fullerene cage, and the molecules also can be encapsulated in cages. So we have the carbon nanotubes, graphene materials, and the properties can depend on many things. The most important things can be the solvent structure, so the host interaction. So many things happen actually, right? The size-based selectivity, the density can alter significantly. So this is just some brief. And in theoretical perspective, we are interested in this mainly 4 categories. So we have the impenetrable and the sharp, and the impenetrable and the smooth, and the penetrable and the sharp, and the penetrable and the smooth. And I have also listed some of the prominent examples in all these categories. So the impenetrable means, the sharp means that there is a discontinuity, the smooth means there is no discontinuity, and impenetrable means it is bounded from above, and that penetrable means it is not that. So quantum dots are 0-dimensional structures spanning few nanometers, and it can contain any number of electrons. The tunability of electronic and optical properties with respect to the size and shape of the dot is the most prominent thing that most people are interested. And the model potentials, the prescribed, are typically like this: an impenetrable spherical cavity, the harmonic potential, or the finite oscillator potential. So the 2-electron quantum dot, for which the results I'll be mostly presenting, is there, but it can also be 3-electron, 4-electron, and there are works already reported in such. So the potential is, of course, the half kr square potential at r less than equal to rc. The k denotes the force constant, and as far as the theoretical methods are concerned, we have perturbation theory calculations, we have variational methods, complex coordinate Schier methods, and also DFT results. So I will present some DFT results. So the starting point is, of course, the Kuhn-Sum equation, and where the psi i's are the single particle orbitals, and the effective potential is given, the partitioned in terms of the Coulomb potential, the external potential, and the exchange correlation potential, and the confinement term, which is the half kr square. So the whole crux of the problem is in the exchange correlation potential, which is the functional derivative of the exchange correlation energy functional in terms of the electron density. So we know that there is an inherent problem in density functional theory about the excited states, And the primary reason is that there is no generalized Weinberg-Kohn theorem for an arbitrary excited states of a many electron system, since in this case we also know that the wave function cannot be bypassed through the pure density. And of course, another big problem is that exact exchange correlation functional for the kinetic energy and the exchange correlation energy in terms of density are not known. We have many approximate and good, very accurate exchange correlation functionals developed, but those are still mostly for the ground state. So the excited states functionals are still elusive. Efforts are being made, but it's still a very open working area. And we also know that working solely in terms of the single particle density may be advantageous for the ground state, but it can be having its own problem for the excited states. So here we adopt a work function method which has been used for many years, and very briefly speaking, exchange energy is simply interpreted as an interaction energy between an electron at R and the Fermi Coulomb whole charge distribution rho xr r prime at r prime. And this expression is given by the equation. So this is the exchange energy. And the exchange potential can be defined as the work done in bringing an electron to the point R against the electric field produced by the Fermi Coulomb hole density. And that is the electric field due to the Fermi Coulomb hole charge density is given by this. And finally, the exchange potential can be written as this line integral. So some of the features of this method is that there is a dependence on also it's an orbital dependent method because the details are omitted. So once it worked out, eventually this can be written in terms of the orbitals. And this theory is for the full exchange correlation potential, but has been mostly implemented in the exchange only calculation and for atomic excited states. So here the difficult orthogonality problem is essentially bypassed. And this is also a non-variational method. So as such, the variational bounds are not operational. And this, as we will show the results, it can be valid for both ground and excited states. And for the numerical solution of the resultant cone sum equation, we have adopted a very accurate, the generalized pseudospectral discretization scheme. And it has been used over the years for various states. It was mainly pioneered by Professor Chu at Kansas and his team. And I started to learn this method when I was working as a postdoc. And thereafter, it has been used by many groups, of course, in our own group itself. So the basic philosophy is to approximate the exact function fx in the interval -1 to n by the nth order polynomial fnx, such that the approximation can be exact at the collocation points, which is the xj. And various kinds of polynomials have been adopted, but our experience and various works have suggested that the most suitable polynomial for the Coulombic singularity problems is the Legendre pseudospectral method. So the Legendre polynomials. So the cardinal functions g, j, x can be written, and thus the primes are the derivatives. So the advantages of this method are that this eventually leads to a symmetrized eigenvalue problem. It's of course a basis set free method, and it's very computationally convenient and easy. And it is also very accurate, and it has been used for both atomic and molecular problems, including the dynamical problems. So there is a nonlinear mapping involved, which is given by this, where is this nonlinear mapping parameter. And so eventually doing some, some symmetrization procedure, which is given by this equation, one can find the transform Hamiltonian in this form. So with this, the equation and this, so this is the that standard solution procedure. So once we construct the grid and we construct the kinetic energy matrix and the potential energy matrix, the Hamiltonian is there, eigenvalue equation is solved, the wave functions are eigenvalues are obtained. So I'm sorry, there is an I missing over here. And then from that, the various quantities, in particular the energies and information measures like Shannon entropy, fission entropy, and etc. are obtained. So as has been already expounded by various speakers, so very briefly speaking, the quantity is entropy is a measure of the uncertainty of a random variable. And we know that information is carried over from one place to another, and one seeks information when there are more than one alternatives, and we are not certain about the outcome of the event. If an event occurs in just one way, there is no uncertainty, and no information is called for. We get some information by the occurrence of an event when there was some uncertainty prevailing before its occurrence. So information received by its occurrence equivalent to amount of uncertainty prevailed before its occurrence. And we also know that lesser the probability of an event to occur, higher the uncertainty prevailed in it. As a consequence, more information will be received after the occurrence of the event. Excuse me. So Shannon entropy is the arithmetic mean of information and given by this expression of this with this logarithm. So it can be for the position or momentum space, and it is also maximum for an equiprobable distribution and minimum for a certain event with probability 1. And we also know that the famous uncertainty relations can also have connection to this SR and SP, and lot of works are already also has happened and still going on. So the Shannon entropy can quantify the density, and in quantum mechanics, it has been exploited to understand quantum entanglement, aromaticity, and various things, including electron correlation. The Fisher information is a local measure and is given by the gradient functional, and it is always greater than the reciprocal of mean square error, and only in case of Gaussian distribution it becomes equal to the inverse of it. It's a gradient functional of density, and its connection to the famous kinetic energy functional, the Weizsäcker functional, and other functionals in the DFT are also very much worked out by various groups. So now I can present some of the results which are obtained from this method. So we are showing the results from the Hookean artificial atom. So it's basically a 2-electron quantum system bound by a harmonic oscillator potential. Most simplistic model for studying the electron correlation effects. And these are also having connection to the functionals in DFT, especially the kinetic energy function. The system behaves as a bound system due to the presence of the harmonic potential, which is why it is often referred to as an artificial atom. And it can also provide a simplified framework to understand the complex system. These are also often called the harmonium atom. So here I show the first result for the Hookean, for the ground state energy of the Hookean. So the force constant and the RC. So as you can see from this figure, so the ground state energy of the Hookean, its monotony increases as K increases. And the ground state energy has a sharp increment for smaller region of RC, right? In this one, the figure B, whereas it almost remains insensitive for a certain particular RC, in this case about 2.5. The nature remains the same for the variation of energy as a function of RC's K. So here the two Ks are given, K 0.005 and K 0.5. Both are for the ground state, and this result is for the exchange only result. That means in our calculation, should the no correlation energy functional was employed. So in the future slides, I will show some results where some approximate correlation functionals are introduced. But this is an exchange-only result. So this is also an exchange-only result. But here, the Shannon entropy is plotted against the K, and the Fisher information is plotted against K, both in the position space. So you can see that Shannon entropy is, for smaller K regions, it suggests that a more delocalized system, whereas it decreases slowly for this K greater than 2.5, which signifies a localized one. And the Fisher information shows rather opposite. It increases monotonically as K increases, and by increasing K, the system becomes more localized. So this is another result for the K is equal to 0.005 and K is equal to RC, with showing the RC variation. Okay, so this is K is equal to 0.5 and K is equal to 0.005. The same for this plot also. This is Ayers and the right side is IR. So as is implied from this plot, so when the K increases, the system actually tends to be mimic it's like a strong confinement situation. And for higher K, the system is more localized. Okay. So from Z is equal to 0, we can now show the effect of nuclear charge. So I now show some results of the helium atom on the harmonic confinement. So in this case, this column shows the K values variation, and this XX is the exchange-only results. These are the two correlation energy functionals employed. One is the simpler Wigner correlation, and another is the LEAP, the Lee-Yang power correlation functional. And these are some of the reference results. And this is for the ground state 1s2, and this is for the 1s2s triplet state. So K is varied from varied for a long range. And as you can see, wherever possible, the reference results and our results are not so bad. The exchange-only results are always very close to the respective Hartree-Fock calculations that has been checked, and it is not mentioned here. But so these results, the reference results, are typically from very accurate calculations or explicit hilarious type methods. So, but we see that our approximate correlated results are also in good agreement with these reference values. So this is for the ground state, and it also goes with the excited state, and for which the results are not so much. So here the variations are shown for the two functionals. We can so out of these two correlation functionals, the results are given only for the LEAP functional, and it is also the helium. So XX results means exchange only, and the LEAP functional results. So the total energy eventually monotonically decreases as K increases, and the system becomes more and more unstable. And these are the results for the 1s2s triplet S and 1s2p triplet P. So we can see that this is the triplet S results, XX and LEAP. This is the triplet P results, XX and LEAP. So these are the Shannon entropy and Fisher information results in the R space. And these are also the results for the same three sets of potentials, the exchange only and the Wigner and the LEAP. So some of the results are available in the free system. So those are given here in the footnote. One can see that. So the XX results are already so much in good agreement, and we see some results which are a little bit different. So that can be due to various reasons. And the IR results are also in good agreement with the reference. So this is plotted, and we can see that this is the Shannon entropy in the ground state, and this is the Shannon entropy in the excited states, 1s2s2p and 1s2s3s. And we see that more or less the similar features are noted for both the excited and ground states. So basically, Shannon entropy diminishes and reflecting a more localization in the system. And another interesting observation is that for higher K region, Shannon entropy for both exchange-only results and correlation functional converges to each other, so signifying that the correlation effects may not be so prominent. It is also true for the plot in the right side. So this is a complementary Fisher information results for the same two states, from the same three states, ground state and two excited states in the plots versus K, and the Fisher information basically increases as K increases. And we see that 1s2s and 1s2p somehow show some sort of reverse traits and opposite traits from each other. So one limiting scenario is the ground state information entropy. So when K is equal to 0, the results lead to the so-called hard confinement domain. So we can see that those results are recovered in our calculations, and this is for the Z is equal to 1, 2, 3, 4 helium isolated series. And this is the Shannon entropy plot, and this is the Fisher plot. And we see that these hard confinement results have been published by us sometimes before, and it is of course the same as we obtain here. And this is a plot, the exchange-only result plot for the with respect to Z, and we can see that value. So these are the various RC, and the plot is against Z. Same for SR and IR. Basically, one sees that SR is larger for larger RC and smaller Z, and IR monotonically increases with Z for a fixed RC, but it decreases as RCs. Okay, so these are some final results for the SR and IR. I think I should skip that to go to the time. So this is for the excited state, 1s, 2s, 3s. We see very similar features as in the ground state, so nothing much. So this part was done by this work function approach of the quantum equation. Now I present some other methods, not only just method, but also to get some more details of the calculations. For example, that will show some of these moments and angular moments, radial moments, and some other properties which are important. So basically, this is a hilarious method, and with having a function of this form, and where the various quantities are listed here, we can see that this is the permutation operator, and the K becomes +1. So these are the details of the method. I think I should not say much. So basically the CI, the linear parameter CI is there in the expansion. And of course the base choice of the basis set is given by this table, which is essentially, so the parameters alpha, beta, gamma, these are the 3 nonlinear parameters, which are quasi-randomly chosen from a one-dimensional box problem by using this Nailor-made optimization technique, and the box lengths are obtained by doing this optimization trick, and these brackets denote the fractional part of the enclosed term, and the basis eventually the one has to deal with these basis integrals, which are done very accurately by us. And so eventually one has to solve this matrix equation, and that will give us the. So here is the result for the helium in the ground state. So one can see that the accuracy. So this is the pre-scenario, and these are the various Ks, and we have gone up to K is equal to 2.2, and typically the reference results are given at K is equal to 2.2. The total energy of helium surpasses its threshold value, which is He+. So we kept our calculation limited to this point. Basically one sees that increment in K elevates the total energy of the system. Here is a plot of the total energy and kinetic energy in terms of K, and we can see that the sharp increment in energy. So this is the total energy, and And of course, kinetic energy shows some sort of parabolic enhancement with K. And of course, the virial theorem is not valid. And here is a plot for the potential energy, the total potential energy, and the harmonic part of the potential energy. So you can see that it's a parabolic decay in the total potential energy, and the harmonic part of the potential increases almost linearly with K. And this is clearly evident as both interparticle. So this is something that we are going to show in the next few slides. So various radial and angular moments have been calculated. And so these are the various, R1 and R12. So the nucleus electron separation, electron separation, and this angle between the electron nucleus and the electron with respect to the nucleus theta and theta 1, 2. So here is a plot for R and theta, and one can see that. So eventually, so the R1, R12, R1 square, R12 square. So all the plots are here. You can see that basically it is all these plots, and here is the theta. So there is a slight, constancy over here, and thereafter it starts to fall like almost like a linear. And all these plots, it says is that it's basically is that it is showing a shrinkage in the triangle form by the 2 electron and the nucleus as K increases. So the localization of the system with respect to the increment in K. And so this is the inner and outer radius plots. So this is the minimum of R1 and R2 and maximum of the R1 and R2. And we can see that R less than R greater than plots are there. So both inner and outer radius diminish as K increases. It also supports the localization of the system with respect to K. So then we have this 1 and 2 particle delta functions. So this delta R1 basically means the probability density of the electron at the nucleus at the quantum dot itself, and the probability density of the electron at the other electron. So this is delta R1 and delta R12. So we see that they both, so this one shows a monotonic increase, and this one remains rather very like an invariant. And this is the radial density plots, 1 electron radial density, which can be obtained from this expression. So so these are given for 3 K values, K0, 1, and 2. And we see that the whole distribution shifts towards left as K rises. So this like this, and which again means that as K increases, there is more localization. And the Shannon entropy and Fisher entropy plots are also given for the 1s2, so helium ground state. So we see that Shannon entropy decreases with K, and the Fisher entropy increases. So it's almost like a complementary nature, and between these two things. So with this, I now come to the conclusion of this part. So we have shown a DFT method which is efficient to describe the behavior of the 2 electron system under the harmonic and hard confinement. And we have shown that manipulation of the electronic properties of the 2 electron system by tuning the K can be a very useful exercise. And increment in K can value shifts basically the downstream energy level of helium atom to its threshold energy value. All expectation values, including the radial and angular, collectively indicate the shrinking in the system with respect to increment in K. So this is also evident from the density distribution plots, which is then demonstrated by the information measures. And Fisher information and Shannon entropy shows conjugate nature in their plot, in their behavior. And so this is a part of the work which we have done for the 2 electrons, but we are also working with the 3 electron and 4 electron problem. And so these are some of the papers which have been published on this field. So Neetik Mukherjee was involved. So this is about the relative entropies. This one is about the harmonic oscillator. This one is about some complexity measures. This one about is the H minus hard confinement, and there are various other papers, I think. So the latest one is this one and this one, which does some work. And I wish to acknowledge the various people who have worked in this group: Dr. Neetik Mukherjee, Dr. Sangita Majumdar, who is currently working as a postdoc in US, Dr. Shantanu Mandal, who just finished his postdoc term here, and he's going to Mexico for he's going to Brazil for his postdoc. Ravina Arya is a PhD student in the third year of her thesis. And these are some of the photos. And I would like to thank you for your kind attention. And I would like to mention one thing before I stop. When I was doing I have fond memories of a collaboration from a professor at UNAM, when I was doing my last postdoc at UCLA, University of California, Los Angeles, and we had a very fruitful collaboration, and in terms of the publications and etc., etc. And with this, I want to thank you for your kind attention.
Thank you very much for your presentation. Now we will have a short break and we will be back at 11:25. That is in approximately 3 minutes.
Thank you so much.
Thank you. Thank you. Thank you, Amlan. Thank you.
Thank you.
Hello, Professor Sen. Good evening.
Hi. Hello. How are you?
I'm good.
Good. I'm waiting.
Welcome back. The next speaker is Professor Vinod Prasad of the Department of Physics, University of Delhi. And the title of his talk will be Electric Field Modified Shannon Entropy of Free Confined H Atom. Professor Prasad, the microphone is yours.
Thank you, Professor Sagar. I'm very privileged to be part of this Golden Jubilee celebrations of UAM, and congratulations to all the team of UAM for such a wonderful work on information theory and confined systems. So I will be presenting my work on, as Robin shared, electric field modified Shannon entropy of free. And the reason is that we know that electric fields modify the properties of the systems. And in addition to electric fields, there are other methods, for example, confinement. And there are some structural parameters which also change the energy levels and the structural properties of the system. And then in case of confinement, change in energy level, accidental degeneracy, incidental degeneracy, all these things take place, and which result in some sort of new properties for due to confinement. As far as external fields are concerned, there are many ways to modify or to induce behaviors which are otherwise not visible. And these fields are external electric fields, static electric fields, and magnetic fields. And of course, there are laser fields. And even combination of electric and magnetic fields are used to induce those changes. As far as static electric field is concerned, star effect is main reason for change in energy and polarizability, dipole moments, etc. And at times, the avoided crossings which occur in case of electric fields due to Stark effect, these avoided crossings play a very important role in many ways. Avoided crossings are those phenomena where atoms of certain category, they come closer to each other and then they start repelling each other. So there is a minimum energy difference where the avoided crossing takes place. And although if you look at the curves, it looks as if the states have just come closer and then behaved, means moved away. But if you look at the with the perspective of wave functions, it is very strange that the atom or wave function before avoided crossing and after avoided crossings, they actually interchange, and that causes the interesting phenomena which are visible otherwise, which are not visible otherwise. So the system which we have considered here is confined hydrogen atom, and then of course a free hydrogen atom, and particle in a spherical box. Particle in a spherical box we have taken into account because when tight confinement happens, the even confined hydrogen atom shows that the as if the electron is in a spherical box rather than in the presence of a attractive Coulomb potential. So this particular case, particular spherical box, is taken to emphasize that behavior and to see if change in behavior is there as far as electric fields, application of electric fields is concerned. So the time independent Swedish equation under consider for confined hydrogen atom and for particle in spherical box. And of course, this we have used atomic units. So this is usual hydrogenic terms. and this BC is common in both the cases, and this is a impenetrable cavity, and RC is the confining radius. So when system is exposed to the electric field, there is an additional term corresponding to that interaction in both the cases, and this interaction is ES. ES is a static electric field, and we solve this Schrodinger equation for this system, time independent Schrodinger equation for these two systems, and I'm writing it in a combined form. So these wave functions psi are obtained like linear combinations of the wave functions psi j's, which are unperturbed wave functions, that is wave function up to this part of the Hamiltonian. And if you put this expansion into this Schrodinger equation and use orthogonality properties of the wave functions, we get a eigenvalue equation like this. And diagonalizing this eigenvalue equation, we get these A's, which are probability amplitudes, and we get the new energy states, which we call dress states or dress states energies. In this particular case, mu ij's are the interaction term of the system with the electric field. So diagonalization of this matrix gives rise to eigenvectors, and which gives the probability amplitude, and probability of excitation from J to the state J from initial state I can be found by this one. And we were interested in studying effects of these avoided crossings, because there have been many studies where, in our case, we are using avoided crossing to see what happens to the Shannon entropy at those crossings. But this particular study of these authors, what they have done, they have used Shannon entropy as an indicator of avoided crossings, and to find out the exact energy difference between these states. For example, in this particular figure, the states taken are, if I talk of the first figure, this one, states taken are 19s and 21p, and second case 19s and 21p is for the total Shannon entropy. So this is the point where avoided crossing is taking place. That is the point of closest distance, and at the states come closer to each other, and then they move away. And in the case of Shannon entropy, we can see that here there is an exchange of, we can say that there is an exchange of entropy. That is, the 21p states entropy becomes that of 19s states, and vice versa. Almost, they are almost same. So before and after avoided crossings, the entropies get exchanged. And same thing happens here. The state taken is different, 21s and 23p, and otherwise behavior is similar. So they have used this one to find out exact energy difference between Rydberg states of the potassium atom. And there is another study. It is very interesting that not only electric fields or the fields which we talk in general, they induce avoided crossings, but there are many other factors. For example, in this particular case, there is a study for interaction between this Rydberg atom, xenon Rydberg atom, with a metal surface. And this particular curve or graph is showing this Z is means one atom is coming closer to the metallic surface, and they are finding out what is happening to other properties of this system. But what is happening in this particular figure is xenon Rydberg states show avoided crossings when the atom approaches the metallic surface. For example, this one is one of the cases. Here we can say this is another case, and here there are many cases of avoided crossing as atom comes closer to the metallic surface. So not only electric field, but other factors are also responsible for avoided crossings. Then this particular there is another example that here these authors have studied localization and delocalization for avoided crossings in a quadrupole quantum billiard. But again, the case is not with the field, not with the electric field. It is with the, they have taken a distorted, distorted billiard ball, quantum billiard, and this deformation, that this epsilon is the distortion deformation parameter. So when they change the deformation parameter, something around this point, avoided crossing occurs, and we can see the point which I said in the previous slide, that the wave function, although energy levels move like this or this one, but wave functions get exchanged. Means this wave function which is here becomes the wave function of the second state at the after the avoided crossing, and the wave function of this system becomes a wave function of the first state after the avoided crossing. And as far as the case of the scenario around avoided crossing is concerned, uh, wave function is a mixture. It is a mixture of both the states, and it depends on the extent of the distortion or the external parameter which is causing the avoided crossings, how the wave functions will look like. So this is another example of creating avoided crossings, and this one is another case where closed and open quantum billiards are considered. Again, avoided in the region of avoided crossings, the wave functions show very different nature. So and reason being that near avoided crossings, wave functions are a mixtures of the states. As far as electric fields are concerned, it depends on the strength of the electric field. That if it's like electric field is strong enough, and if levels come closer enough, then there is a chance of 50% of a mixture of the initial state and the final states. So, and because of that mixing, the phenomena at the avoided crossings become very interesting. And later on, I'll take another case of the time-dependent field, where we take a laser field and then show that not only the intensity but the frequency also causes those avoided crossings. And of course, it depends on the number of levels being considered, because interactions do happen, because we are taking of the static electric field or the laser field. So what happens, wherever when we take large number of states, so large number of avoided crossings happen, and due to that large number of avoided crossings, at times it becomes very difficult to identify the final states. So to avoid that confusion, we have taken limited number of states, and we have taken two particular cases. So these are the all preliminaries. So I think we need not to discuss or talk about these points. So what we have done is we have taken the case of the sudden entropy in position space and sudden entropy in momentum, and then total sudden entropy and scope information, KL distances, LMC complexities, etc. And we all know that they are used in many they have many applications. For example, uncertainty relations, localization, delocalization, entanglement, cross correlations, and computing, cryptography, and many other applications are there. So first part, we have taken the case of a particle in a spherical box. We have taken finite number of labels. For example, we have taken a bunch of 1s, 1p, 2s, 2p, and 3s, 3p states. We have calculated the spectra, that is energies of at various confining radius, and then sudden entropy. of these labels as a function of electric field and confining radius. So this table, this is long table, but my point was just to show that electric fields required to observe avoided crossings with respect to the confining radius depends on the depends on the confinement radius. Not only the electric field will induce the avoided crosses, but strength of electric field and the confining radius, they play an important role. For example, when system is quite loose, means when confinement is quite weak, then even smaller electric fields change energy levels quite drastically, and it happens for all these states considered here. But for a tight confinement, as I said, energies are too high, so these fields are not for these fields to induce changes in the energy levels will not be possible, or to induce changes in these energy levels, the fields required will be enormous. That is not possible. The fields, the kind of fields not possible in laboratories. And we have compared the results with the quite simple with the numbers available, and this table shows that how entropy changes with the electric field, and for different levels, of course, as these cases, and of course changes in entropies are not very large, but just introduction of electric field induces a significant change in the total Shannon entropy. Once this change happens, then changes are very smooth, and we will see later on that after certain electric field, the Shannon entropy almost becomes constant. A reason being, then those at very high fields, the systems behave as if they are not mixed with the field, or they behave very differently, as if they were free. So this is the case of a very weak confinement. So there are significant changes in the entropies, and this curve I'll just show that how energy changes with the electric field and with the confining radius. So these are for different states. This is for, I suppose it is visible. This is for 1s state, 1p, 2s, and 2p state. This is what I just wanted to show, that with the introduction of the weak electric field, for 1s state, there is a very sharp change in the entropy, and after that it becomes almost constant, and there is significant change in this entropy or this one. But for higher fields, all of them become almost constant. We have not shown it here, but at higher fields they become almost parallel to the to this state. And we can see that for very tight confinement, these are the cases of confinement. This one, red one, is for tight confinement, radius is 2. This is for 6, blue. Green one is for 12, and black one is for 20, and then 50. So for tight confinement, there is hardly any change in the total Shannon entropy of the state. And these are for 1s, 1p, and 2s, 2p states. So we can see that this behavior is similar to that of hydrogen atom, which I will show later on. And these are the behavior of Shannon entropy in momentum and position space for different electric fields. We have shown it as a function of confinement radius. These are the Shannon position space, momentum space, and total Shannon entropy for different states. For example, this is 1s, this is 1p, 2s, 2p, and like that. And this curve shows I will be talking about this one, that with confining radius and with the introduction of the electric field for small electric field, we can see that there are many ups or kicks in the Shannon entropy. And with the strength of increase in the strength of the electric field, there are subtle changes, right? So reason being, I will show this one. Uh, the reason for those changes, as I said, that there are avoided crossings taking place between different states, and these avoided crossings, according to these avoided crossings, there are changes in the total Shannon entropy, even for all these radii which we have considered, and with uh, increase of the confining radius, because system becomes very almost free. So what happens, even with the smallest of the electric fields, there are many uh, 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 many crossings happening, and these are reflected in these curves. So as I said, that with the introduction of the parameter which is causing the avoided crossings, be electric field, be it be a deformation parameter, as in case of open billiard ball case. So whatever the parameter may be, the wave functions change the nature. 1s becomes, if I talk of only two states, 1s and 2p, so 1s becomes 2p and 2p becomes 1s. So entropies also change accordingly. So these are the curves for KL distance, which are similar to those. So for confined hydrogen atom, there is an additional term. So this Coulombic term plays a role up to certain distance, but and wave functions and energies uh, are a bit different compared to the uh, particle in a spherical box because of the Coulomb potential. But tight confinement, the energies for example, for RC.1, the energy for hydrogenic atom is 468 point some atomic units, and in case of particle in a spherical box, it was something around 493. So energies are almost similar, and so we expect this behavior under tight confinement to be similar as far as effect of electric field is concerned. And these are the results which we have computed with few results available. Although there are many results available, but to compare with means to quote all of them uh, was not possible. Of course, when uh, we sent the review article to Professor Robin, so all those references will be taken care of. So this table again shows that even in case of hydrogenic system, in case of weak confinement, the changes are significant as far as energy division is concerned. Even for 1s, 2s states, we can see that states are strongly influenced by electric fields. So this behavior is for three states and for three cases of electric. This is for without any electric field. This is for weak electric field, and for us, I will say this is with uh, a bit stronger electric field. So with the induction of the electric field, we can see that there is a change in the behavior of the entropy. That is entropy of the this 2p states. It gets a kick something here at 2 points, right? At this point and this point. With the induction of electric field, it crosses over the entropy of 2s state. So, and these are the Shannon entropy in position and momentum space for same set of states. This is the energy. This curve shows that how energies vary as far as variation as far as electric field is concerned for a fixed confining radii. So lower states are strongly affected compared to the higher states. So in another case, we have taken sixth level state. As I said, that number of states also play a very strong role in identifying the or in identifying the avoided crossings or identifying the entropy changes in entropy. So in case of six states, we have taken 1s, 2s, 2p, 3s, 3p, and 3d states. So we can clearly see that the changes are happening at many places, and these are the points where those crossings take over or wave functions change nature. So this is the case of six state for different electric fields. And then we try to identify where states are actually happening, means those crossings are actually happening. For example, this curve shows the 1s state moves like this, 2p moves like this, and 2s goes this, and 2s 3d and 3p, and all at all the points wherever avoided crossings happen. For example, at this point, the crossing between these two states take place, and for a weaker confinement, radial confinement, the crossings are much more clear, and same thing happens with the entropies. So later on, what we found was that the states form these electric states form. Sorry. For different
5
electric
minutes.
fields. Oh, sorry. Oh, so I will just come quickly to another case which I was interested in. This I will skip. We have studied this endothermically and this confined hydrogen atom, and we have shown these phenomena. But what I was interested was showing that what happens when the time dependent electric field is introduced. And in this case, the dress states, although they have time dependence here, but when it comes to the calculation of entropy or probability density, this time dependence goes up due to the orthogonality properties of the wave functions. So system, as far as entropies are concerned, it again becomes time independent, and then frequency also becomes a parameter in addition to the electric field to induce those avoided crossings. So again, in this case, as case with the static electric field, we have taken two particular cases, and laser frequency is varied up to this point, and we have of course taken weaker electric fields. So these two graphs show three state, and this is four state case, and on x-axis this is the frequency of the laser field, and lower panel is showing the probabilities of excitation to higher state or the states of crossings concerned. So for example, at this point, the probabilities for this 3D and 3P state, they go very sharp peak, and here this is two photon case, and this is one photon case, this is two photon case, and this is three photon cases, and same thing happens, same kind of peaks can be observed. So we need to identify the number of photonic transitions taking place and the points where these avoided crossings are taking place, and accordingly we can guess that the change of entropy or will take place. And in case uh, these 1 photon, 2 photon are the photonic transitions between different states. For example, in this case, 1s and 3D, it is a 2 photon case, and the resonance happens at this particular frequency. And for higher means, if you include a larger number of states, then there are many photonic transitions happening, and these transitions. This is a bit enhanced view, but according to the means, what I just wanted to show that in this case the variations are very smooth. This is one case, this is another case, and this is third case. This is actually, this is between, it should have happened between 1s and 2p state, this particular one. But what is happening? It is happening between 2p and 3d states. Reason being that after first crossing, 3d becomes 2p, and after a certain frequency, 2p becomes 1s. So these are the interesting features as far as changes in entropies with respect to frequency. And of course, we have taken a very weak electric field. So our point is that we can use laser interaction with the system to induce a information switch. For example, here the entropy is switched between 3D and 2p state. So we can say that we can have an idea of an information switch using laser system, atom laser system. So as I'm short of time, although I just wanted to show few results. So these are our KL distance, and they show similar behaviors number with this is another example. So these are conclusion. The effect of Coulombic potential, Hartwell potential field plays important role in different regions. And as I said, that for very high tight confinement, sun and entropy tends to the value of particle in spherical box. And this one I just wanted to show. So thank you so much for giving me this opportunity. Thank you for patience.
Professor Prasad, Vinod, thank you very much for your presentation. Thank you.
Thank you, Robin. Thank you very much.
Yes. Un abrazo de Mexico. Is Professor Fuentes, Ivette Fuentes, is she on the call? Ivette? Professor Fuentes?
Hello.
Hi.
Can you hear me? Oh, hi. Yeah, I was not allowed to unmute, but it's working now.
Okay. So if you could just please share your screen with us, just we can make sure.
Okay.
Yeah,
is that working? Does it look good?
Yeah, it's just a lot of screens. We don't have the we're not.
We have the presentation view, presentator view or something.
Yeah.
Sorry, I didn't hear that. Excuse. Hi, can you hear me?
Yes, we can still hear you. We're here.
Oh,
Yeah. So
yes. You said there was a problem.
Yeah, we can see the presentation. We see the whole presentations, but the first slide, I think, it's if you could just.
Okay. Yes. Oh, that's working now? Okay. Oh, well, perfect. Okay.
Okay, so we will continue on. Our next speaker is Professor Ivette Fuentes from the University of Southampton, University of Oxford, and the title of her talk is Studying the Unification of Quantum Theory and General Relativity Using Bose-Einstein Condensates. Professor Fuentes, you have the microphone.
Thank you very much. Thank you very much to Humberto and Rodolfo and the rest of the organizers for this very nice invitation. And very especially, I want to congratulate everyone at the Universidad Autónoma for this, for your 50 years. I mean, that's really like a wonderful, wonderful thing. And I am very honored to be invited. So thank you very much. And also not to go with Manuel Solano, who agreed to swap. I had a flu the whole week. So I hope my throat is well, because I'm just coming out of it. So, well, I'm very happy to be able to give this talk. So I've been working for many years using quantum information theory to address problems in fundamental physics. So I started out around 2005 using sort of techniques I had recently learned from my PhD in Imperial College on entanglement and so on, to address problems in, let's say, apply some of these techniques. It was quite early on black holes and on the Unruh effect. I also studied entanglement in curved space-time, like looking at some simple models for the expansion of the universe and so on. So that's sort of like where I come from. But that was already many years ago, almost 20 years ago. So what I have become more interested in very lately is in the unification of quantum theory and gravity. But I come from a very different perspective, as you will see. What I do is nothing to do with string theory or loop quantum gravities, or a little bit as our own take on this problem. And I'm not going to talk today about the full extent of our work because it's not finished yet. So we're about to publish something that I think is super exciting. So my talk today is more as a teaser and take you through some of the logic of how we've gotten to develop some new models. So let me start from the beginning. So there are many interesting questions in fundamental physics that many of us are very interested in. And I wrote here a few that I think are among my favorite. For example, what is the nature of dark matter? Is dark energy driving the accelerated expansion of the universe? What is the physics? I just was informed it's recording just now. I hope it was not a mistake. What's the physics that dominates the universe at early times? And does the equivalence principle hold for quantum systems? So these are very interesting questions. But underpinning our difficulty to find answers to many of these questions is the fact that quantum mechanics and general relativity are incompatible. So like I said, I was interested in applying techniques of quantum information to address questions in fundamental physics. And by that, we developed new techniques, and we learned many other techniques and learned how to bring them together, like quantum metrology and quantum field theory and curved space-time, that sort of thing. But when I realized that what was really underpinning all the difficulties to find answers to these very interesting questions was that this fact, then I became more interested in actually looking into this problem from a different perspective. So let's take a step back and go to quite, fundamental questions about the two theories and compare them for a moment to see where the problems might lie. So while in quantum theory, we have that time is absolute, and indeed, like space and time are very different notions as in classical physics. So if we look at the Schrödinger equation, it has a first derivative in time, but a second in space. And the Schrödinger equation treats space and time in completely different ways. So time is a parameter, but positions they're quantized and so on. So they're treated with operators. So from the beginning, from the onset, the Schrödinger equation already treats space and time in a complete different way. And then we have the superposition principle. So we have that particles can occupy two, for example, distinct positions at once. Now let's jump to relativity. And in relativity, time and also length are not absolute anymore. They're observer dependent. And actually, one of the most radical things that we learned from Einstein is that space and time are not really different notions. They actually belong together in a higher dimensional object that we call space-time. And then we get other effects. So for example, if we have a mass that curves space-time, then we can look at two different points in the space-time, and we find that time flows at different rates in different points. So then if you think about putting these two things together, having, for example, a superposition of a particle in two distinct locations where time flows at different rates, well, we don't actually have a theory yet that allows us to address these sort of physical situations that we can imagine in a consistent way. So in my opinion, the most interesting question to think about at the moment is if a massive system can be in a spatial superposition. So we, in many experiments at the moment and for many years already, we've seen that it's possible to put particles in a superposition. Actually, these experiments, the double slit experiments started with electrons, have already 90 years. So for 90 years, we've been able to put a massive system, an electron is a massive system, in a spatial superposition. And we know that, this is allowed by physics. We have observed it in the experiment, but if we take seriously also general relativity, we know that mass would bend space-time. So of course, in the case of an electron, this is negligible, and same for atoms. But now imagine having the same situation with bigger and bigger masses. This would mean that we would having the gravitational field, so the space-time, in a superposition of two different configurations. So is this possible? No. So and why we might be able to think that it might be different to the electromagnetic case is because gravity is the only force that has an equivalence principle. So there is no reason why to think that it would behave like other forces. So we know that the electromagnetic field can be in quantum states, so basically can be in these superpositions. And we've seen this in many experiments. So quantum optics is a field in which, there's many experiments have been going on for many decades now, and that proves some of these things. But with gravity, it has been, as you know, much more complicated to test in the experiment. So I stole here a little way of putting things from Roger Penrose, that he asked, should we quantize gravity or gravitize quantum physics? So by this, he means quantize gravity would mean to keep the principles of quantum theory and then modify general relativity accordingly to somehow make them compatible. Or gravitize quantum physics would be to keep the principles of general relativity and then modify quantum theory. And Roger thinks that we should be doing the second case, because he finds that quantum mechanics is already problematic because of the measurement problem. So that's why he would favor, let's say, a program that would keep GR as the fundamental theory and then change quantum theory to find a way of making these two theories compatible. I think most likely both will have to be modified. But I think what is very interesting and what we should be focusing on now is on trying to find which are the principles that are indeed fundamental from the experiment. There is a lot that can be done theoretically and mathematically, and we have seen, like the development of string theory or loop quantum gravity for many years now. But I think we all recognize that the need of having experiments that tell us what principles are fundamental and how to develop theories based on experiments is really important at this point. But it's not just that it's important. I think the exciting thing is that it's now becoming possible. And I want to tell you more about how. Before moving to the next slide, I also want to mention that recently there has been other suggestions, like, for example, from my colleague Jonathan Oppenheim, who's brought forward this idea of post-quantum, that he proposes combining classical space-time with quantum physics, and he shows how one would be able to come up with a theory that does that. And it's been quite controversial, but what I really like about Jonathan's work is that he makes concrete experimental predictions. So he says, okay, if he built this theory, and if my theory is correct, then this is the experiment that should verify the theory. And I think that's where we want to bring this field to the point where we make theories that we can test in the experiments. And I think I'm very excited because I think we're at the brink of this. So I found this slide on the internet, and I liked it very much because it made me sort of reflect on how people might have come up with ideas in cosmology before we had the instruments. So it makes me think about humans just looking at the sky and looking at the stars, and from there, just with our instruments, our eyes, trying to make sense of where are we and what's out there, and how difficult it is without the instruments. And then, Galileo was the first to propose that we should use a telescope and point it out into the skies. And it's amazing to learn that actually people didn't want to do it. Many people refused to do it, which is really interesting. And then, the telescopes have developed very much since then. We have now amazing instruments. And with these instruments, now we can learn that the universe is expanding. We can look really far into the early universe and so on, and make much better theories. So I think this slide is to point out the importance of having instruments and experiments in order to make progress. And if you think about also the small, the Greek came out with the idea of the atom. And this is something that I find amazing, because the whole sort of paradigm and the whole way that we understand science is through thinking that atoms and matter in that sense is fundamental and fields, and from that everything is built in our universe. And as I said, the Greeks came up with this idea of the atom, but it actually took so long to be able to see and prove that atoms existed, right? And we went through centuries of just developing ideas and so on until, instruments started to be developed, and we have now microscopes, and we can look into the microscopic world, and we can start doing very serious atomic physics now. But I think it's really fascinating to really take a step back and think about all the time that took from the Greeks coming up with the notion of the atom to actually being able to do atomic physics using instruments. Now, when it comes to the scales, what we expect quantum effects and relativistic effects to interplay, we have nothing. We're completely blind. So we're worse than actually that story that I was picturing of having humans looking into the sky with their own eyes, because at least, they have their own instruments, their eyes. But when it comes to those scales, we have been completely in the dark. Well, sort of. We now have some new experiments, but we still now need theory to catch up. And let me tell you a little bit about that. I'm going to take like a little pause because my throat is drying out because of the cold. Okay, so what I've been trying to do in my group for all these years is focus more on coming up with experiments that we could do in order to learn things at the interplay of quantum mechanics and general relativity. So that's been a little bit my take. I'm also like a theoretician, but instead of joining in, let's say, the theoretical efforts that my colleagues were making, I kind of felt that I would perhaps it would be wiser for me to do something different. And the different thing that I kind of focused on was more, okay, so if we now take all the advances in quantum technologies that are taking place, and I started to realize how sensitive these technologies are, can we start inventing new instruments to look into these scales that I was just mentioning, where we've been in the blind. So in my group, we focus in 3 areas. I'm going to focus on the third one for this talk, but one would be long-range experiments. So when I was a PhD student, the experiments taking place to demonstrate entanglement and distribute, let's say, entanglement in an experiment and do teleportation and this sort of things were tabletop experiments. Since then, they become sort of possible to do longer and longer range experiments. And nowadays, it's possible to distribute entanglement across thousands of kilometers. And one of the things I've been working in the last years is showing that relativistic effects start to kick in at this scales. Actually, that is easy to see, because when you have a clock on Earth, the clock ticks at a different rate than a clock in the satellite. And actually, our GPS uses that in order to get to make corrections and get the precision that we get with GPS. It's necessary to take into account relativity and the relativistic correction to the time dilation. Now it's not unimaginable to understand that if you're now having distributing entanglement at these scales, that this also becomes relevant. So people were already taking some relativistic effects into account, but more just like special relativistic effects, just the phase shift that you would get. However, with a series of papers that I've written with my group, we show that it goes beyond that. And we describe this using the Schwarzschild space-time of the Earth around, to describe the space-time of the Earth, sorry. And then we used quantum field theory in curved space-time to describe the propagation of wave packets in between satellites and between different links. And we showed how the curvature and other general relativistic effects have effects on quantum cryptography and quantum teleportation and so on. So this is, like I said, a series of papers that we've been working on for many years now, but I won't touch on that today. But this is an example of a technology that has already reached relativistic scales, only that the relativistic effects are mostly ignored. I think we were among the first to start pointing out, hey, these experiments and the theory that we use to describe these experiments need upgrading, because you already are at scales where relativity kicks in. And I think quantum field theory in curved space-time, which hasn't been, by the way, demonstrated in experiment, is at least as a start, a good way to start looking into these situations. Then the next one, if I have time, I'll say something about it, but I'm not very sure, is a high sensitivity. So quantum clocks have a precision of 10 to the minus 18. It's just really amazing, the level of sensitivity that quantum technologies reach. And with a clock, you can see a quantum clock with the current sensitivities. There's papers claiming that they can see time dilation, not at the scales of thousands of kilometers involving the satellites, but already within a millimeter. So, excuse me. So there's been some beautiful experiments. One of them was by Dave Wineland, who showed that there was time that he could demonstrate time dilation within 33 centimeters. But this distance has now been reduced, like I said, to the millimeter scale. So again, we're in a situation in which you start seeing relativistic effects in quantum experiments. And we need to develop the theory now to be able to explain, again, these situations in the lab. And now I want to focus on the last one, which is large mass, because I was saying before that I find that in order to understand fundamental physics, the question that I find the most important is if we can have a space-time in a superposition with a massive system, but in a stable way. So like I said, we know we can do this with atoms, or with small particles, but if we have more and more mass, is this a stable situation or not? And in that case, we haven't reached the scales where relativistic effects would become important, but I want to tell you what is the development in this area and what are the interesting questions. So, well, you are probably familiar with this proposal by DLC and Roger Penrose, that it's gravity that actually the culprit that we don't see quantum superpositions in the classical world. So, of course, a very important line of research is explaining how, if we start from a quantum theory and how at the scales of atoms and small particles, we have quantum theory, but then in the classical world, we don't see quantum superpositions. What causes this transition and how can we explain it? And DLC and Roger proposed that it's gravity which is collapsing the wave function. So DLC came up with this notion in a purely classical way. I'll say a little bit more in the next slide without needing to allude to general relativity. But Roger Penrose came up with this discussion, let's say, in which he argues that spatial superpositions and the equivalence principle are not compatible. Therefore, spatial superpositions of massive systems should be unstable. So something that's very interesting is that then both DLC and Penrose came up with this same formula, which is called the gravitational self-energy of the difference, which is the culprit for the collapse of spatial superpositions. So like I said before, DLC came up with this same notion from a purely classical argument. So he was classical and says that no general relativity. So he was thinking about what would be the time scale involved in the collapse of spatial superpositions. And he proposed that if we now looked at the mass and thought about the work it takes to, let's say, separate two identical masses in let's say the energy that it would take to separate these two identical spheres, that is given by the gravitational self energy of the difference. And he said the time of collapse should be proportional to that quantity. Now, from a complete different point of view, Roger arrived to exactly the same formula, only that Roger did get started with relativistic considerations. So the formulas that they arrived to are identical up to a 1/8 pi. So Roger's formula has this 1/8 pi difference because it comes actually this 8 pi from general relativity. And then Roger said, okay, he gets this energy uncertainty, and via an uncertainty principle relation, he concludes that the time of collapse should be given by h bar over the gravitational self-energy of the difference. Now, here there is something that well, I've been telling Roger that needs to be revised because the energy uncertainty that is being used, it holds only for unitary evolution. And actually, this is something that my student Ethan and my colleague Pablo, who actually gave a talk here, also pointed out and noticed, and we went into looking more into it, and we indeed found that, you know, that this uncertainty principle holds for unitary evolution. So if you're assuming that something collapses the state, this is no longer a unitary evolution. Either you have a stochastic process or the coherence process or something like this that makes the evolution no longer unitary. So strictly, this doesn't apply. But I think in any case, it points out that there is an energy uncertainty that makes the system unstable. And I guess it gives you some sort of idea that there should be a collapse somehow, although strictly speaking, we can't use exactly that formula. So we can calculate the gravitational self-energy of the difference for a sphere with uniform density. So this is actually a calculation that Roger Penrose did. And you find that the gravitational self-energy of the difference depends on big G, the mass squared, the radius of the sphere, and the separation B of the superposition. So it's interesting in this formula as B becomes larger and larger and larger, the gravitational self-energy of the difference doesn't change much. But what one can see is that it's maximized just when the two, like this, well, it's the same sphere, right? But the sphere is just touching with itself in the superposition. That is when this is maximized. So how massive can systems be currently in experiments? So the record is held by Markus Arndt, who's at the University of Vienna. So I had the honor of being 3 years in Vienna, working as a visiting professor. And I had like the opportunity to interact with not only Markus, but all the other amazing experimentalists in Vienna. And well, it's really amazing what they do in his lab. So the record for a massive superposition is he uses molecules, usually like carathane and that sort of molecules. And they have around 2,000 atoms. Now, I recently went to a talk that he gave in December with an update, and apparently, I don't know if this has been like already published, but he did announce that it looks like they managed to push this to another order of magnitude. So, but that's where things are at. And I want you to see in a few slides what is actually the prediction that Diossi and Penrose does on the mass on when we should be seeing superposition. So you can see how far we are from being able to test this conjecture that gravity collapses the wave function. So other really important progress in this direction is by Markus Aspenmeier, who's also in Vienna, and he managed to take nanoparticles made out of silicia. He cools them down to the ground state of a harmonic oscillator. So he cannot put them in a spatial superposition, but he can cool the particle to the quantum regime with quite massive systems. So he manages to get beads that have 10 to the 8 atoms, something like that, which is very impressive. And now also one of my colleagues at the University of Southampton, Henrik Ulbrich, he also has with some of his colleagues some really nice results on taking this sort of very small particles and being able to measure gravity at these very small scales. So this is classical gravity. There's nothing quantum yet, but he's clearly getting at scales where eventually there might be some new physics or some interesting things happening. There's many experiments by many groups, and some examples of other systems include nanodiamonds, mirrors, little rods, membranes. There are many, many different experiments, but as you can see, these all involve solids. Excuse me. So I met Roger. Sorry, my voice got very funny. Many years ago, and he was telling me about his work on the collapse of the wave function. And back in the time, I was working on how to use Bose-Einstein condensates to test things in quantum field theory in curved spacetime. And he became interested in my experimental proposals using BECs. And then I just became curious to find out how could we test some of the ideas of collapse of the wave function using a BEC. And the reason why I became interested in this is because, well, BECs are a collection of many atoms. Usually, experiments involving BECs use rubidium. That's like, well, there are many atoms, but that's one of the most common. And they were at the moment using things like 10 to the 5, 10 to the 6 atoms. So they all come down to the ground state where they become in a joint collective quantum way. And they all condense into the ground state. And then in some cases, although people were not very interested in very large systems, I looked in the literature and found out that, I don't know, that a group had created a BEC with 10 to the 8, 10 to the 9 atoms using sodium, and even 10 to the 10 using hydrogen. So they can have many atoms in a quantum state, not in a spatial superposition, but in a quantum state. And well, what I noticed is that most of the problems that people were getting in being able to prepare spatial superpositions is the temperature. So temperatures for solids are very difficult to get to very low degrees. On the contrary, with the Bose-Einstein condensate, you can achieve incredible cold temperatures. The record is half a nanokelvin or something like this. Is really amazing. And I thought, well, maybe these very low temperatures could be an advantage. And I thought, okay, let's take this a little serious and see what could be done with a BEC. So I was very lucky to write a paper with Roger in this direction. So we looked at how could we propose an experiment using one of these systems. Now, the problem is with a BEC is that you would have to prepare a state that is known as a new state. So this means like n particles on the left, nothing on the right, plus 0 particles on the left and n on the right. And these states are incredibly fragile because in the moment that you lose one atom, you collapse the whole state. So you want the state to collapse because of gravity, not because you lost an atom or an environmental effect. So, you know, at this stage, it was sort of interesting to look at this, but not very realistic. But it was very interesting to see what were the advantages, the disadvantages, and the constraints. But it's really this paper that inspired all the work that we're doing right now, which I think really managed to make quite a bit of progress. So I'm going to jump in because I'm already see that I've gone very slow and my time is running out. So, well, we just studied different configurations and different geometries, different, not only the uniform case, but BCs are not really uniform densities, so more realistic densities and so on. And we studied all the different sources of decoherence, so 3-body recombination, 2-body losses, and so on. And then, well, we concluded, and this is not exclusive to BEC, this is in general, that in order to see the collapse of the wave function due to gravity, you need around 4 × 10⁹ atoms, and you need to be able to keep them in a spatial superposition for a second. This is really out of any possibilities experimentally, because as you can see, the record right now with solids is with the molecules that are, I don't know, 2,000 atoms, maybe now 20,000 atoms. But here you can see that you need 10⁹. And also doing this on a BC with how fragile the new states are really becomes not manageable. Then Diossi took a step even further, and what he did is that he made a model to describe the collapse of the wave function, which doesn't conserve energy. So that I don't like from the theoretical point of view, because it's stochastic. So it's like a spontaneous collapse model. And now the thing with this is that this model has been largely disproved by the experiment. There was an experiment done in 2021, which basically falsifies this model. So I was talking to Roger about this because it was all over the news, like, oh, Roger Penrose has been disproved. And Roger was like, no, because I just said there would be a collapse, but I did not propose this model. He's not very supportive with the point that the model doesn't conserve energy and so on. So this made me think about alternatives. And this is where the exciting thing really starts, because we were able to come up with a complete new model that solves some of these problems. And we're about to bring a paper out that I hope will revive this idea that gravity might be collapsing the wave function, because our model is consistent with the experimental results that masses don't radiate. I didn't go into the details of that, but anyway, so that has been my group and I work with Pablo Barberis, who also spoke in the conference as well, fighting 2 years with developing a complete new model from scratch. But what our model does, this is like again the teaser and just a little preview, is that we have a model that makes predictions that are testable with state-of-the-art technology. It shows how superpositions reduce in a finite time, but it does this in a complete energy-conserving way. And we also recover in a limit the gravitational self-energy of the difference that was put forward by Diossi and later on by Penrose. And also our model can be extended not only to a particle in 2 locations, but to many particles in 2 locations, which allows us to then come up with experiments that are much more realistic. And that is because when you have a BEC, because it's not a solid, it's a fluid, particles can tunnel from one location back and forth. And what this does is that instead of the only sort of interesting quantum states that you get, which would be a superposition of left and right, here you have a very rich family of states that you can get. So, for example, you can prepare two-mode squeeze states and so on, that are actually states that people have already been prepared in the experiment. But what people had not done yet would be, because it's not possible with the other situations, is study how gravity would affect on such states. So that's one of the other things that we've done. We've developed new techniques to study the effects of self-gravity on these, let's say, different sort of states that that the theory before didn't allow for. So this is my collaborations. We work with Philippe Boyer and Chris Westbrook, who are experimentalists, and they are helping us develop the experimental proposal. Our paper that I said we're preparing is not only the theoretical new model, but it's also a very concrete experimental proposal as well. And Ethan Campos and Kia are both my PhD students who come from UNAM. This is actually, I put together a whole team, because looking that this is going to be, I think, a very interesting new step, and I can already see how this can develop in different directions. So I made sure that I put a very strong team of students together to push this forward. And here you can see this is Ethan and Kia. Kia is a mathematician, so a pure mathematician that came to group to the team because we required techniques that are new to us, and he's been very helpful. Hector is my PhD student who's now finished, and he's going to stay as a postdoc to help us develop the model. Melanie just joined. She is a PhD student at the University of Oxford, where I also supervise students, and she's an expert in numerical methods. And Abdul is a current PhD student who works in philosophy. So one of the nice things that we've done is that we spanned everything from starting with Melanie, that worked in the lab in Mexico in a Bose-Einstein condensate, and she helps us bridge with the experimentalists, but she's going to be doing numerical work. And then Hector and Ethan and I have a similar, let's say, training. We're physicists. And then we have Kia, the mathematician, and then ending with philosophy, because we're interested in all the philosophical implications of our models. So I'm really proud of this team. Most of them are Mexican, and that's because they have very good mathematical skills. And yeah, we're having a lot of fun, and I hope that we'll be able to present our results soon. So I'm going to finish here. I was going to say a few more things, but I think I took too much time in this. But anyway, this was the, let's say, at the heart of what I wanted to talk about today. I didn't get the 5-minute notice, but I guess my time is there, no?
You have more time, Professor Fuentes.
Oh, I have more time. Okay, good. How much more time do I have?
5 minutes.
Okay, so let me see what I can do with 5 minutes. So I was just going to talk about my previous work. So just to show some of the ideas that my group was putting forward before we came up with this new direction. And like I said, I was thinking about using Bose-Einstein condensates to learn something about the interface of quantum and gravity. So this is with contributions of my previous group. So when we think about measuring gravity, usually what people use are gravimeters that are consist of many particles that come into an interferometer. But in a sense, they're a single particle detector, because although you throw 10 to the 5, 10 to the 6 atoms in an interferometer, each atom goes through a different trajectory at a time, completely independent of the others, and they interact and they interfere. and the interference pattern depends on the local gravitational field. So the atoms are usually in free fall, and that's how we measure gravity. And the precision depends most importantly on the time squared flight, so inversely to the time squared. So if you think about wanting to measure gravity in a very precise way, you need to make bigger and bigger detectors. And that's people have actually done that, and there are a number of really impressive experiments where these long baselines are achieved. But we proposed a different way of measuring gravity by, instead of having the atoms in free fall, trapping them. And when you trap them, they interact. So in the other proposal, sorry, not proposals, those are very serious experiments. In the other scheme, the atoms are not interacting because interactions are actually create errors. But in this case, on the contrary, you want the atoms to interact because these give rise to phonons. And phonons are quantum excitations as well that are actually, that's what our work showed, very sensitive to space-time distortions, to space-time changes, and so on. So basically, the idea was to put forward the idea of doing interferometry in the frequency domain instead of in the space domain, using the phonons. The phonons are sharp in frequency, although they're completely delocalized in the size of the BEC. And we came up with a sequence in which you would do interferometry, but now in frequency. So if you can think about interferometers, sorry, reaching the precision by making them bigger, that's because the superposition is in space, so you need a large baseline to make them sensitive. Now we're doing interferometry in frequency, so we don't need to go big. What we need is to live long. So that's the price you pay. In one, you have space, you need to make them bigger. In this case, you have a frequency, so what you need the states to live longer. So we use this idea that we call the frequency interferometry to propose a number of different things that you could measure in gravity. So the first idea was, how could you measure high frequency continuous source gravitational waves? That's how we got started. And then we saw that we could use the similar idea for different gravitational effects, including dark energy and dark matter and so on. So this was a whole line of research that we were following before the work I just mentioned. And basically what it is a quantum version of a Weber bar. So Weber bar were these big metallic cylinders that were used to try to detect gravitational waves using resonance. But the phonons are in the classical domain. And in a BEC that you get 10 orders of magnitude colder, you have also phonons, but now in the quantum domain, where you can squeeze them and prepare them in quantum states that make them very, very sensitive. So I'm going to jump this because, well, this is just pointing out that you can use them to detect some signals that you might get from dark matter. These are some models for dark matter that use sort of some bosonic description of the dark matter. So we were studying how, in what scales could we, in principle, propose a detector using the idea of frequency interferometry. Well, one of the advantages of using a BEC to detect things like that is that BECs you can make in many different shapes and configurations, and in principle you could have many in the planet. So we were pointing out that you could use coincidences and so on to increase the sensitivity and being able to distinguish what the signals are and so on. And the most recent work that we've now been focusing on is showing that you can use a BEC also to test different models for modified gravity. So there are different proposals out there. Some are more popular than others, but we take a very sort of agnostic point of view with the models. You give us a model and we tell you using RBC, how could you test for modifications of the model? And one of the things that I am most proud of is that I just got a patent for this idea, because we then applied it on how to miniaturize a gravimeter. And one of the things that I like very much is that to show my students and so on, that you can focus on some fundamental questions that are very important and very exciting to study, but then you can also use what you learned to propose things that might have applications in the real world. So we got this certificate now for the patent in Europe, and we have also been accepted in the US. So we have a little part of the group also focusing on commercialization of quantum technologies. And I'm now really going to finish now with really also exciting news, is that we managed to raise money to test some of our ideas in the lab. So together with Philippe Boyer and Chris Westbrook, we're building a new lab, and we're going to be hiring PhD students and postdocs to help us test some of our crazy ideas in the experiment. So I thank everybody for your attention.
Professor Fuentes, thank you very much for your presentation.
Thank you.
So the next presenter, Neetik, Professor Mukherjee.
Hello, sir.
Okay, we will move on now with our next presentation. Our next presenter is Professor Neetik Mukherjee, Department of Chemistry in Medicaps University in Indore, India. The title of his talk is Information Entropy in Confined Quantum Systems. Professor Mukherjee, you have the microphone.
First of all, I would like to thank to giving me this opportunity to present my work in this prestigious conference of commemorating the 50th anniversary of UAM in application of information theory in natural sciences. I would also like to grab this opportunity to thank my supervisor, Professor Amlan K, Pfizer, Kolkata, to giving me the opportunity to work on this field. And also, I show my sincere gratitude to Professor K.D. Shen. He's a living legend, and his work in confined quantum system and also in information entropy gives me the motivation to work in this field. And also, finally, not last but not the least, Professor Vinod Prasad, with whom I have discussed many times and learned a lot from him. So to begin with, the topic of my discussion is information entropy in confined quantum systems. Today, my primary objective is to show how information-based uncertainty measures, particularly Shannon entropy, has helped to explain several quantum mechanical phenomena in confined quantum system. To cite a few examples, I will focus on symmetric and asymmetric double well potential and the confined hydrogen-like system and some plasma systems. To solve at the beginning, I should mention that for the double well potential, we have used a couple variational technique to get the eigenvalue and the eigenfunctions with whom we have calculated the Shannon entropies. And In case of a confined hydrogen atom, we know that it can be exactly solvable, and it has got a hypergeometric function, and that hypergeometric function requires energy to get the exact form. So we get that exact energy from the generalized pseudospectral method, and then use that energy to the wave function and calculate the information entropy. And finally, for the plasma system, we have used generalized pseudospectral method. So to begin with a basic mathematical expression of Shannon entropy, we all know that the Shannon entropy quantifies the uncertainty of a system, and it actually the arithmetic mean of Shannon entropy. It's arithmetic mean of uncertainty, and it also provides the famous BBM inequality, whereas the Fisher information gives us the information, and it also quantifies the total information. Onikezko energy, meanwhile, describes the order, whereas when Onikezko energy is higher, system is more ordered. On the contrary, when system is more disordered, Shannon entropy will be higher. Next, the Onikezko-Shannon complexity, which is a combination of two competitive quantity, where Shannon entropy measures the disorder, and Onikezko energy measures the ordered system. And finally, the uncertainty principle. Why we have mentioned the uncertainty principles with this? In the first of to do our discussion, we will try to compare the BBM inequality with the conventional uncertainty principle. Although we know that the BBM we can starting from the BBM inequality, we can reach to the Schwarz inequality, which is the original by which we can prove the conventional uncertainty principle. But in reverse direction, starting from the uncertainty principle or Schwarz inequality, we cannot reach to the BBN inequality. So let us begin the first example, that the information entropy for the symmetric double well potential. This is the most simplest form of a double well potential, where we have alpha x to the power 4 minus beta x square. In this potential, the interesting part is that both alpha and beta plays a competing effect on this potential. When we increase when we increase alpha at a given beta, then we can see that with increase in alpha, the barrier height decreases, as the barrier height for a double well potential is beta square by 4 alpha. And with increase in alpha, this barrier height decreases. On the contrary, the classical turning point or the classical boundary region decreases. Whereas for beta cases, the barrier height increases with increase in beta, but the classical turning point also increases. So due to this competing effect, there arises quasi-degeneracy between the, as this is a symmetric potential, between the parity state. That means one odd parity state and one even parity states. So our point was to check whether the conventional uncertainty principle is able to explain this quasi-degeneracy and the localization delocalization effect associated with this potential. So at the beginning, we study the delta x, delta px, and their product for the ground and fast excited state of this potential. And we found that for the ground, for all the three cases, or the delta x cases, delta p cases, and delta x, delta p cases, there are certain minimas, and they are not able to explain the fact that why this quasi-degeneracy is arising and how localization is happening. So next we move to check the probability density of the particle within the classical region, and we found that in that region, the probability of finding the particle within classical region initially increases with beta at a given alpha, then after that it suddenly decreases. Similarly, for fast excited state, it's also again increases, and after some time it decreases, though the decrease is not that sharp like the previous ground state one. To this when we started calculating the Fisher information, and found that these are the Fisher information plot for the first fourth state of a double well potential. The first two plots are for the left one. First two plots explain the position space Fisher information, where the middle two are for the momentum space Fisher information, and last one is for the total combined, the product of the position and momentum space Fisher information. And we see that the both position space and momentum space Fisher information decreases initially with increasing beta at a given alpha, and throughout our calculation we kept alpha fixed at 1, and with increase in beta this value of the Fisher information gradually decreases, attains a minima, then it increases, and after a certain point the Fisher information value of both ground and first excited state as well as second and third excited state become equal. So first point in the Fisher information, which we have not seen in delta x delta px measurements, the explanation of quasi degeneracy, that in this region their energies are almost same to, and also their Fisher information values are almost same. And also that decrease in Fisher information indicates that with increase in beta there is a certain point where the particle gets maximum delocalized, and after that beta the particle again started localizing. To this end we move to study the Shannon entropy of for the same four states of a double well potential, and here also in this plot we can see that these two are the position space Shannon entropy for the ground first excited, second excited, and third excited state, and this one for the momentum space Shannon entropy for the ground first excited, second excited, and third excited state, and last one is the sum, the famous. And in all these four cases the BBM inequality is obeyed. Now here we can see that with increase in beta value, the Shannon entropy gets increases and attains a maxima and then decreases, and also after a certain characteristics beta value, the Shannon, like the Fisher information, the Shannon entropy of these two states are equal. This clearly explains the behavior or the competing effect of beta, that with increasing beta initially the particle gets delocalized. After a certain point it reaches a maximum delocalization, and then its delocalization decreases or it's gradually getting localized. And also the momentum space Shannon entropy plot explains the same, that the decrease in momentum space Shannon entropy again indicates the delocalization of the system in position space. So from this Fisher and Shannon entropy study we can clearly say that the Shannon entropy, the information entropy can explain the behavior of symmetric double well potential and the quasi degeneracy cases. Also, apart from that, to get the further information, we studied the Onisescu energy, and we see that the Onisescu energy also decreases with increasing beta, indicating maximum disorder, and this disorder, and again it increases indicating orderedness. That means what we conclude in the previous two graphs, that the information that with increasing beta, system first gets delocalized, reaches its maxima, and again getting localized. But from the conventional uncertainty product, we have not get such information. So they are unable to explain the quasi-degeneracy pattern in double well potential. So to this end, from the symmetric double well study, we can conclude that information-based measures are able to explain the quasi-degeneracy in double well potential. To understand the better extent, we move to the asymmetric double well potential, where we have added a asymmetric term of gamma x in this symmetric double well potential, which introduces an asymmetry in the right hand side of the potential. And if we analyze these graphs and also these two graphs, we can clearly see that the odd symmetry state, that was n1, n3, n5, even Odd quantum number states are localized in deeper well, whereas even quantum number states are localized in shallower well. And also in ground, there is quasi degeneracy between 2 and 3 state and 4 and 5 state. To get more insight, we have analyzed their energy and as well as their wave function and conjecture certain rule, and then we see again how this conventional uncertainty principle as well as the information based measure explain this phenomena. If we see this graph, this the bottom panel or the bottom row of the graph shows the variation of energy at three different parametric values of beta of 5, 10 and 15, where 5, 10 and 15, whereas the middle graph shows same for the beta equal to 10, beta 25 and beta 30. And all these cases we have measured the results keeping alpha equal to 1 and varying gamma, and we can see that at beta 10 onwards there is staircase like pattern in energy. This indicates that there is a certain characteristic gamma value at which the energy of some states become equal, and after that they again separate from each other. So that's like avoided crossing like situation arises for this system. And but ground state is always non-degenerate. So to this information we move to study the wave function of this system at six different bound for 6 different bound states. The ground again the lower panel indicates the ground states of the symmetric one where gamma is 0, and if in all these cases for the ground state, first excited, second excited, third excited, fourth and fifth excited state, all these 6 states the wave function is evenly distributed. That means if we here we have plotted the wave function, but if we plot the probability, then we can check that the probability of finding the particle in either side are same. But once gradually from the second panel we increase beta value, that means gamma value, then we can see that that distribution is not that, it's the symmetry is lost and ground state is always in the left panel. And from our potential graph we have seen the left side of the potential is a larger well, so ground state is always in larger well, whereas for the other states it depends on the beta values to change each position from one well to another. And actually with change in values they oscillate between one well to another and finally localize, just like for the ground first excited states it's initially in the shallower well, then again move to the deeper well and finally reside it. And for all these states, if we finally check that they are finally resides in deeper well states. So to generalize this, we have conjecture the distribution of these states in these two well, that if n equal to k. Now the question arises, what is k? Actually when we check the energy value, we have seen that this staircase like situation arises at certain characteristics gamma value, and this staircase like situation appears after same interval of gamma values. In our calculation, when we kept alpha equal to 1, this gamma value is always 2. So and the next gamma value where the second staircase like situation arises is gamma equal to 4. That means the delta gamma, the change in gamma is always 2. So based on that delta gamma, we check based on that we conjecture a parameter k, which is ratio, nothing but a ratio of gamma and delta gamma. When this gamma and delta gamma become integer, the ratio of gamma and delta gamma become integer, then we see a quasi degeneracy in double well potential, and when this ratio is non-integer, quasi degeneracy is no longer seen. So based on these results, we can see that if n, that means principal quantum number, is greater than k, then two possibilities may arise. When if n greater than k and k is also integer, particle in nth state is distributed in both ways. That means either both in I1 and 2. But if k is fraction, there will be four different possibilities. Both n and both n and the integer part of k. If both n and integer part of k is even, then particle is in first well, that means deeper well. If both n and k is odd, then also it's in deeper well. But if n is even and k odd, then it's in shallower well. Similarly, if n is odd and k is even, then again is also in shallower well. So, and finally, when n is less than k, particle is always in deeper, a larger well. And again, based on the results, we have also conjectured the quasi-degeneracy situation when the quasi-degeneracy arises. When n equal to k, and this table actually clearly shows that how the particle distributed in double well potential. So k, when k is an odd positive integer, an odd n state will be quasi-degenerate with its immediate higher states. If k is even positive integer, an even n state will be quasi-degenerate with its adjacent higher states. So no, quasi-degeneracy will depend on the values of k. And when k is fraction, there is no such quasi-degeneracy. And when k is greater than n, nth state cannot be in quasi-degenerate state. And always, and that's why the ground state is always non-degenerate. So based on these observations, we tried to study whether the both conventional uncertainty principle and the Shannon entropy can explain the quasi-degeneracy and such phenomena in asymmetric double well potential. And in this case, we have studied this for 4 different states and several beta values, and find that for all the beta values, the delta x plot of delta x shows a jump at characteristics gamma value where we have observed quasi-degeneracies. And these are the observations that we can see that there are jumps. This clearly indicates that that for asymmetric cases, the delta x, that conventional uncertainty principle, can explain the behavior of where quasi-degeneracy will arise. Similarly, we move to study the variation of gamma at certain beta, and we see for 4 different states, and we see that in both cases they can explain the behavior of localization and delocalization effect for asymmetric double well potential, which we have not seen for the case of symmetric double well potential in this conventional uncertainty principle. And finally, we have also seen similar behavior for Shannon entropy, and Shannon entropy jumps at that characteristics gamma value where quasi-degeneracy arises for double well potential. So contrary to the symmetric double well potential cases, in asymmetric double well potential cases, both conventional uncertainty principle as well as the BBM inequality can explain their quasi-degeneracy nature. So now we move to the information entropy in a confined hydrogen-like system. So in confined hydrogen-like system, we took the confinement in different form. In previous cases, by changing the parameters, we can localize or delocalize the system in either of the way. But in case of confined hydrogen atom, we trap the electron within a certain radius. That means instead of taking the boundary from 0 to infinity, we have took the boundary from 0 to RC. RC is the critical radius where the probability of finding the electron is 0 beyond that RC. So, and varied RC to check and calculate the Shannon entropy for confined hydrogen atom at two states, one is and two states. The confined hydrogen atom is interesting in this context that due to introduction of this confinement, that there occurred the rearrangement between the energy states. and this leads to the drastic change in their several properties. So we study the Shannon entropy for the fast excited for the 1s and 2s states, and for the fast row we can check that when RC is 0.1, the Shannon entropy for the ground state is negative, and it is not only for the ground state, also for the fast excited state the Shannon entropy is negative, and this negative value for both in 1s and 2s state continues up to 0.8. This is an unusual observation because Shannon entropy define the uncertainty, and which is usually can be expected to be positive, but in this case we observe negative value. Not only negative value, if we compare the values of Shannon entropy of the 1s state and 2s state, we can check that the Shannon entropy value of the 1s state is 6.2445, whereas for the 2s state it's minus 6.4475. And if we check it for Shannon entropy for 1s state is 0.52 at RC equal to 1, whereas for the ground state, for the fast excited state, it's 0.45. This means that the Shannon entropy of the fast excited state is lower than the Shannon entropy of the ground state. That is very interesting, and from this observation we can conclude that the impact of confinement on fast excited state is more than the ground state. And to explore these, we have plotted the Shannon entropy of the first few states of the at different L values, and seen that the Shannon entropy for a given Shannon entropy decreases with increase in N. With increase in RC, this pattern slightly changes the energy. The two states has, in these cases, the two states has more energy, more Shannon entropy. Similarly, if we go to the momentum space, we can see that the reverse trend is observed. So from this observation for the confined hydrogen-like system, we have seen that the impact of confinement on excited state or higher energy states are more compared to the ground states or low-lying states. Next, we move to study the information entropy in plasma system, and in this case we took two different well-known plasma system. One is the Debye-Hückel plasma, which has the form of minus 1 by r e to the power minus lambda r, and the second one is the ECSAP, the exponential spin Coulomb potential, where the potential have the form of minus 1 by r e to the power minus lambda r cos lambda r. This lambda is a screening parameter, and we all know that with increase in the screening parameter, the number of bound state decreases for a given plasma. And in this case, we have studied the same for the 1s, 2s, 2p, 3p, 3d, and 4d states to check how Shannon entropy behaves at the point where the states gets deleted. And in this case, we have found that at the point of deletion, when the states become bound to free, then the Shannon entropy jumps occur. The jumps in Shannon entropy occurs. And we have done this calculation at the four different Z values. And what conclusion we got? That with increase in Z value, the point of deletion or the critical lambda value gets right shifted, but in all these cases there is a jump. There is a jump in Shannon entropy indicating the deletion of the state. Similar observation is also seen for the exponential spin Coulomb potential, where again with the point at the point of deletion or at that critical point, Shannon entropy jumps abruptly. So this again indicates that Shannon entropy can explain the fact that in a plasma system with increase in lambda value, there is a deletion in state. So in conclusion, I have cited some of the examples where where the Shannon entropy is efficiently explained several quantum mechanical phenomena for the several quantum mechanical phenomena. Okay, so now for the acknowledgement, I would like to thank ACRB and CSR India for the financial support, Ayers Kolkata for giving me the opportunity and the facilities, and finally my supervisor, Professor Amlan K.
Thank you, Professor Mukherjee. The next talk, I think Professor Ayers is on. Professor Ayers, are you available to continue? Okay, so we're back. Our next speaker is Professor Paul Ayers of the chemistry department at McMaster University in Canada. And the title of his talk is Information Theoretic Approaches, a Personal History. Professor Ayers, you have the microphone.
Thank you, and I want to thank all the organizers for inviting me. I found this a little bit awkward. It took me a very long time to decide what I should talk about. And maybe to explain why it took me a long time. I'm looking at the people who are in this meeting, and they're real information theory people. If you like, they're like skilled carpenters. They really do information theory. And I don't think of myself as an information theory person, right? It would be sort of like inviting one of us to a calculus or a linear algebra conference. We might use it, but do we really consider ourselves experts? So if many of the audience is skilled carpenters, I'm a somewhat unskilled carpenter. And I'm really going to tell you something about my history and try to make it entertaining, but I'm not going to pretend that I use information theory as anything other than just a tool to get something done. So the one interesting thing is that in some sense, my first exposure to information theory happened when I was about 5 years old. The person who brought information theory to density functional theory was Steve Sears, who was a graduate student of Robert Parr. And when Steve graduated, my mother, who was the chair of a chemistry department, hired him. And when he came to work, he didn't have a place to live. And so he lived in my parents' house when I was about 5 years old. And I have on good authority from my father, who was an organic chemist, that he and my mother, who was a spectroscopist, talked a lot about information theory at the dinner table. And so I was exposed to information theory from the time I was about 5. I will not claim that I understood any of it when I was 5, but my father says I understand as much as he understood from back then. So that's... When I really got interested in this was around 1996. I was just beginning graduate school with Robert Parr, and 2 other people who are in this room right now, Shubin Liu and Agnes Naj, were working with Parr in this area about moments of the electron density. And one of the questions that showed up was, do various sorts of moments, are they enough to actually determine a density functional? So can you write a density functional as a moment functional or not? And what properties do the moments have to have in order to do this? And so there's a very rich literature on moments, but once you start doing unconventional moments, it becomes much less clear as to whether or not it works. And so there was a little trick that Parr and myself came up with, which is we would maximize the entropy subject to the constraint of the moments and see whether or not there was any residual entropy left, or whether imposing the moments fully specified the electron density. And so here's an example. For example, you could use the density power moments. And if you maximize the entropy subject to some value of these moments, then you try to maximize it, you take the functional derivative, set it equal to 0, and you get an expression. And then the only question is there any freedom in these Lagrange multipliers? Do you really need to optimize them, or are they fully specified by the density? And in this case, as long as the density is bound, you can rewrite your log in this little trick. And then you realize that all of these Lagrange multipliers are uniquely specified with some arithmetic, admittedly, in terms of the electron density, which means that these moments fully specify the electron density. And so that was something that ended up being a little useful. It was the very first time I used information theory. At the same time, or a little bit later, Roman Nalivosky was visiting Robert Parr, and they pioneered what we would now call the information theoretic approach to atoms and molecules. And the philosophy of this was to choose atoms and molecules that maximally resembled the atoms in the periodic table. We'll talk more about why this was a sensible thing to do, but it's very intuitive that we trust the periodic table as chemists. Let's make sure our atoms and molecules look like them. And then the question was, how do you define resemblance? And their idea was you would minimize the Kobeck-Leibler divergence between the density of the atom and the molecule and the density of the isolated atoms, that is the atoms in the periodic table, subject to a constraint that the atoms and molecule density add up to the molecular density. And if you do that, you get a beautiful formula. And my only contribution to this work at the very beginning was to basically make Roman and Bob a little bit disappointed when I pointed out that this formula was exactly the Hirschfeld atom, and it wasn't actually a new type of atom and molecule. It was just a new derivation of an old type atom and molecule. And to understand this, and I've given the original reference to Hirschfeld, which came, more than 20 years before Roman and Bob's work. Here's lithium chloride. And you can approximate it by just adding up the density of the lithium atom and the chlorine atom. And then if we think about what the predicted molecular density would be, well, we'd say it would be the sum of the lithium and the chlorine atoms. And so we just divide by that sum, and now we'll get a weight for the lithium and a weight for the chlorine. And this is the way that Hirschfeld originally proposed it, but you derive this formula mathematically from the information theoretic approach. And so in this sense, we now know that this chlorine atom resembles the chlorine atom in the molecule, or the chlorine atom, the isolated chlorine atom, as strongly as it possibly can in the Kullback-Leibler sense. And if you compute this, you get charges. A classic thing about Hirschfeld charges is they're smaller than we would normally like as chemists, but you get something that's sensible. We expect them to be smaller. We're trying to find a chlorine atom that resembles the neutral chlorine atom in the periodic table. So we expect the charge to be a little bit closer to neutral than we would expect chemically. One of the beautiful features of this, though, is that these atoms are really solid in terms of level of theory and basis set. I'm just giving you here a bunch of different basis sets, and you'll notice that the spread in the charge as you go from a relatively crappy basis set to an extremely good basis set is almost nothing, right? And so that's a very good stability property. It's something that, say, Mulliken or Levdine population analysis would definitely not give that good a result, right? Why is this important? And the reason it's important is that by doing things in this, we get what you would call maximum transferability. So what this means is, because our atoms resemble the atoms in the periodic table, that means their properties will also resemble the properties in the periodic table. Now, you could pick out one specific property of the atom, and you can match the atom to the atom and molecule, and you would get something different. But if you want to, on average, get properties of the atom inside the molecule to be as close to the isolated atom, you need to minimize the norm. And in fact, you can show that the Hirschfeld atoms do minimize the L1 norm. The other thing that's maybe even more explicit is if you have the property of some atom in isolation and you want the property of an atom in a molecule, if you do the Kullback-Leibler, you can prove that you can write the atom and molecule in exactly this sort of Taylor series where the expansion variable is this quantity, which you recognize as the Kullback-Leibler non-directed divergence, right? And this quantity, of course, is small if the atom is close to the atom and the molecule is close to the reference atom, which means the series converges very quickly, which means that the properties of the atom and the molecule are close to the properties of the reference atom. And this is one of the beautiful things that's very specific to Hirschfeld. So at this point, I thought I was done with Hirschfeld, but Patrick Bolting got me interested in it again. And this came from something that you might think, which is when I did this lithium chloride, maybe I should have chosen the lithium as lithium plus. That would have been a more chemical choice than choosing the neutral lithium atom as the reference state for lithium, right? And one nice thing is you can choose lithium plus, and you'll get, of course, very different charges, but that's still very stable with respect to basis set. But why not choose, say, some other charge for the lithium atom? You could choose lots of different charges for the lithium atom. Any of them are technically okay. Mathematically, it's just which of the various atoms or ions do you want to use as your reference? And this is a problem, right? There was an arbitrary choice inside Hirschfeld, and we'd like to somehow get rid of this arbitrary choice. And that's what Patrick Bolting and myself did. Our choice was just, we choose the charges of the proatoms so that they're the same as the charge of the atoms. It was a very simple procedure. We would just go through, we would start with 0, and then the next time we would choose the proatom to have, say, a charge of 0.5193. Then we would redo this procedure, and we get a charge, we plug it back in, and we just iterated until convergence. But in the literature, there is a giant number of different methods that have been proposed, all of which are just addressing this problem. How should you choose the charges of the proatoms, or the form of the proatoms? All of these are just sort of special cases of that, right? They're just choosing the proatoms in some special way, right? And that isn't very satisfying to me. There seem to be too many choices here. And about this time, a graduate student in my group decided that she really wanted to think about the Hirschfeld partitioning mathematically. And so Farnaz Haidarzada started really looking at where does the Hirschfeld partitioning come from? How really general is it? And then the formal structure also was being looked at together with Tom Verstraelen. And there's a giant soup of references here because this is something that's been going on for quite a while. But we'll walk you through it. But I wanted to deal with the paradox here, which is there isn't a right answer, right? You know, if we think about physics, and I think a lot of us like to think about physics, everything is clean. Like a substance just has electrons bound by atomic nuclei, and what you do is you solve the Schrodinger equation, and then you create, you know, you compute the energy, the geometry, response properties, thermodynamic properties, kinetic properties, anything like this, you can directly compute it. There's no ambiguity. But in chemistry, we have this language where we have atoms and functional groups that are linked together by bonds, and we would like to somehow characterize these things, but we don't have an equation to solve. There's not something like the Schrodinger equation that you can solve and get the bond order or the charge on an atom. And therefore, we have choices that we're going to have to make. And so here I've given a list of some of the properties. I put stars beside the ones that have actually been successfully described using information theory, just for people's curiosity. But nonetheless, understanding these concepts is really important. As a chemist, we can't imagine doing chemistry without the idea of atomic charges and electronegativity and steric effects and bonding and things like this. Right. And so there's a strategy. It was actually something that I did in my very first paper on atoms and molecules. And the idea is we're going to choose some axioms. We're going to list some traits that we want our chemical concept to possess. Then we're going to try to find a mathematical reification of that concept, right? So there could be that we don't have enough axioms, in which case there might be a lot of methods that work, or maybe we have too much and we overburden our concept with too many expectations, in which there may be no method that's possible. And then once we've done this, we can critically assess the method, right? And the reason that this is appealing to me, number one, is it adds some rigor. Instead of arguing about what everyone's right flavor of Hirschfeld is, instead you say, well, we're going to discuss the axioms and the assumptions we're using. So if you want to disagree with the assumptions that I'm making, then that's fine, and we can have an intelligent debate about it. I don't want to argue about the formula. I want to argue about my initial assumptions and get more constructive discussions out. So with that in mind, here are the axioms I would propose for atoms and molecules, or for partitioning, right? I want it to be universal. So I want to be able to define it for anything and any type of computation, right? So I'd like to be able to define it for, say, a quantum Monte Carlo computation, not just a density functional theory computation. I like it to have a foundation in quantum chemistry of some sort, and I would like it to have some nice properties. Ideally, it should be elegant, as in it's relatively simple to describe. It should be unique, as in there's only one answer. It should be size consistent, so that if I give you two systems and they're very far from each other and I partition them, the partitioning doesn't depend on the fact that there's another system. And it should be bias free, in the sense there should be no human ability to change what's going on. I like it to be variationally optimal. That's going to be very convenient. That's why I say it's both mathematical and computational. And we'll talk a little bit about why that's important later. It needs to be computationally robust and efficient, because if it's not, then the method isn't going to work in a practical sense. And then finally, we need to be sure that it's chemically robust. Similar molecules should have similar atoms. When you just do a rotation around a bond, so some sort of conformational change, our charges and atomic properties shouldn't change very much. Associated with that is atoms and molecules should be localized. They should be centered on an atomic nucleus and not go too far away from it. And we should get very good electrostatic potentials, because one of the main uses for atoms and molecules is for predicting, is for parameterizing force fields, for example. So those are my axioms, and you can disagree with me about them, or you can like them. It's really up to you. But based on these axioms, we're going to try to do something. And the first assumption we're going to make is that we're going to do a real space partitioning of the electron density. So it's not going to be like Mulliken or Levdine. It's going to be something that's real. We've worked some on orbital partitioning too, trying to use the same axiomatic approach, but it doesn't come from information theory, and I'm not going to talk about it today. And our atomic densities then will just be some weight factor by the molecular density, where the weight factor is a partition of unity. Once we have an atomic density, then we can get all of its properties from density functional theory or some sort of subsystem quantum mechanics. And so that's one of the advantages of this. And so I've just given a list here of different forms of partitioning, all of which fit into this framework. Of course, we have to choose one somehow. Right? So we're going to go back to Bob and Roman's original assumption. We're going to choose atoms and molecules to maximally resemble the atoms and ions in the periodic table. But then we're going to try to think more generally, which is, how do you define resemblance, right? And instead of using the Kullback-Leibler divergence, we're just going to say, let's just think about a divergence more generally, right? And the key things for a divergence are that it's always non-negative, and that it's zero only if the density and the reference density are the same. So in this paper, we prove that if the divergence measure is a local functional of the atom and molecule and the reference pro-atom densities, then the Hirschfeld partitioning comes only if the local functional is an F divergence. And an F divergence has this form, where F is a convex functional with F of 1 equals 0, right? So this includes Kullback-Leibler, but it includes a lot of other things too, right? But then we said, what about non-local functionals? And we couldn't come up with a really nice description for non-local functionals. So the Thales, the Renier, the Sharma-Matau, and the super extensive divergences all end up being functions of a special type of F divergence called an alpha divergence. And so for these, it turns out that because the alpha divergence, which is an F divergence, gives back the Hirschfeld partitioning, these do also. It's just a chain rule on this function G, basically, that gives that proof. And so here we have the Thales and the Renier and the Sharma-Matau and the super extensive divergences all written down explicitly. They're just formulas. I don't see anything especially sacred about them, right? We could make something even more general called an H divergence. The H divergence has this general form. And in this case, Hirschfeld is obtained if the numerator is an F divergence. So this phi1 has to be complex and phi of 1 equals 0. H has to have H of 0 equals 0. That gets that when the atom and the proatom are the same, that you end up with 0. And it needs to be monotonic. And then this denominator needs to be greater than 0. If it was ever cross 0, then you would have an explosion in this. And you need to make sure that the second derivative is less than or equal to 0. So it's non-convex or essentially concave, right? Once you go beyond this form, we couldn't find other things that gave back Hirschfeld atoms. So at this stage, we felt like we'd done a pretty good job of finding all the possible soup of methods they gave out for Hirschfeld partitioning. And it's a very, very general class. There's something very special about Hirschfeld partitioning that's not specific to Kullback-Leibler. It's not specific to local functionals. Like, it's not specific to F divergences. It's not specific to lots of other things. And in fact, all the other cases that we could find where we could do the math explicitly, at least, always gave non-local atoms. So it seems that The Hirschfeld is a very special choice once you want to have local atoms that come from optimizing a divergence. Right? So the next theorem was that when the Hirschfeld partitioning comes out of your divergence, then the best pro-atoms can be determined by minimizing divergence between the molecular density and the sum of the reference atom densities, or the pro-molecular density. And so this gave a prescription to choosing the best pro-atoms that's now variational. There's the arbitrariness of where do these pro-atoms come from has been eliminated. Instead, you just have to optimize whatever parameters you use to specify your pro-atoms. And there are different strategies for doing this. Two of them are sort of based on these two papers, but we'll talk about one specific one in just a few moments. So this, again, can be any sort of divergence. And depending on the divergence you use, you will get different choices. And that is unpleasant, right? I wanted to have a unique solution. And right now I am not there yet. But let's go on for a second. So our way of choosing pro-atoms is very similar. We're going to choose atoms from the periodic table, just linear combinations of atoms. We're going to assume our atoms are spherically average because isolated atoms we think would have spherical densities. We're going to choose any charge state that we want. We could technically include excited states too. We've tried it. It doesn't change the results very much. It makes the optimization much harder. And I think it's reasonable to say that I want my atoms in a molecule to look like ground state, neutral atoms and ions and atomic ions. Right? And so at this stage, we just have to determine the optimal pro-atoms by a convex optimization. And that's beautiful in the sense that convex optimization means there's a unique solution. It also means there are really efficient numerical algorithms for this. And so now we have a nice numerical problem. Unfortunately, we still have this problem that there's a giant number of different choices here. I haven't even thought about the non-local choices that would also be possible to put into this. But then we're saved, because then we were able to prove that among all the F divergences, the only size-consistent one is the Kullback-Leibler family, or the extended Kullback-Leibler more generally, right? And there's a beautiful result that once you do this, that the atoms in a molecule and their reference atoms will have the same charge. So you get the Hirschfeld I property back, but now it comes out of a variational procedure. And once we put in this extended Kullback-Leibler divergence, the molecule and the pro-molecule have the same charge automatically, and we don't need to constrain it. So this is a beautiful convex optimization. You don't have to necessarily choose the coefficients to be non-negative, but I think it's reasonable to say we're taking some weighted average of possible atoms and ionic states, right? So intuitively, this makes sense to me. Otherwise, you have to be very careful with your optimization. This is a very robust procedure. It achieves my elegance criteria because I'm literally writing the entire procedure in a single line in 1/4 of a slide. Right? So what do the results look? So I'm going back to my lithium chloride example, and I just want you to look. I give the lithium charges, they come out, I think, reasonable. There's a lot of basis sets here. They show a little bit more variation than they used to, but most of it is because of this one outlier for the double zeta case, right? Once we look at the actual contributions, we'll notice that in general, this procedure only chooses a very few of the ions. We gave this every choice. We had lithium anion, lithium plus, lithium 2 plus, lithium 3 plus is 0, and we allowed it to have a 0 density if it wanted to give some to that too. And you'll notice that you basically see something very intuitive, which is that the lithium is really close to just lithium plus, right? So it's a really close to lithium plus result, right? So that's our an intuitive thing that the main contribution to the reference atom is from lithium plus. Okay. So again, this ends up being intuitive, and in fact, this happens all throughout. You may remember at the very beginning, I said, well, Kullback-Leibler has something to do with the L1 norm. And the L1 norm always gives sparse solutions. And so that's what's happening here, is this is giving a sparse solution. Most of the coefficients go to 0, only a few. I can't remember any case where there were more than 3 that were non-zero coefficients. And the other thing is now we're very stable with respect to basis set. So there's a lot of stuff on this slide, but I just want to point out, for example, that Hirschfeld, we already saw that Hirschfeld was really good in terms of basis set stability, right? So this is including a, augmented and doubly augmented all the way from double zeta to 5 zeta. Hirschfeld is great. Hirschfeld I is terrible. Iterative stockholder analysis, terrible. Minimal basis, iterative stockholder, better, not great. Something like electrostatic fitting, natural population analysis, not great. Here are 2 different flavors, well, 3 different flavors really, of this procedure. And you notice that the basis set stability is very, very good. And if we decorated this, well, the other thing to say is the first one of these lines is Hartree-Fock, the next one is B3-Lip, and the next one is omega B97XD. And so also the method stability is very good. So this is very stable with respect to basis and with respect to method. So we put this into a big database. There's actually a much bigger database than this one, but I'm going to show you these because nitrogen atoms tend to be evil. If we just look at what's happening, if you look at Hirschfeld charges, which are too small, we sort of correlate with them, but the slope is bigger, which is good. It means our charges are getting bigger. If we look at Hirschfeld I charges, which we know do crazy things, you'll notice that they're Hirschfeld I charges, sometimes they're nitrogens that have almost a -3 charge, right? And in fact, one of the molecules we took out of this set was in Li3, and within Li3, the charge on the nitrogen was like -3.4. So even below -3. There's a good correlation with electrostatic fitting charges, which is a good thing. And then once again, it does the same thing. Sometimes natural population analysis predicts a charge that's very, very negative, unphysically negative, and this causes all sorts of problems. And we don't end up getting that. We end up damping out this stage scale. Maybe because of that, we get really good electrostatic potentials. It's especially true for charged species. So many of these methods do pretty good for species that are neutral, but once you go to cations and anions, they start to fall apart. And in this case, this new method that we call additive variational Hirschfeld actually does a very good job, almost as good a job as straight electrostatic potential fitting, which you wouldn't be able to actually beat. Right? They're literally fit to make this quantity as small as possible. We said that things should be conformationally stable. So what we did here is we just rotate around the angle. It's this angle C1, N7, C9, C12. So it's this angle right here. And we just twist this around. And what you'll notice is the electrostatic fitting charges go crazy. Iterative stockholder analysis charges a good bit more than you'd like to. All the other charges here end up being very solid, right? Hirschfeld, all of these Hirschfeld flavors basically give beautiful, very minimal conformational stability. That's a chemical property that's being satisfied. So one other thing we can do is we can start constraining charges. So we can start trying to force charges to have a certain value. So actually, this is just looking at different at a different atom. So once again, things are stable. And electrostatic fitting is not so good, but these methods are super stable. To constrain the charges, this is something that we like to do when we're parameterizing force fields, because the dihedrals are, well, they're unpleasant to reparameterize. So we're going to fix the charges on the backbone atoms, and we're only going to allow the side chain charges to change, right? And once we do this, we can get, once again, good conformational stability of the other charges that we haven't optimized. This is the reason that I wanted to have a variational method, because with a convex optimization, it's very easy to put on constraints. I just add a Lagrange multiplier, and now I have a constraint on my convex optimization. And so it's very convenient in terms of being able to do things with your charges, to be able to say, what if I want to force the charge on some atom to have a certain value? So with that, we're getting to the end. So this additive variation or Hirschfeld method, I'd say achieves most, if not all, of our goals for partitioning molecules into atomic pieces. There's still some things we're working on. I'm not sure I wouldn't say that this is the method, but I think it's beautiful that the entire procedure fits, in this third of the slide. We're thinking about generalizations to like promoted atoms, so excited states, to doing spin densities instead of normal densities, and things like this. So that sort of is where the future is, right? I'd like to go back to my list of properties. So I've listed some of the methods here, and I've made a chart of what they do well and what they do wrong, right? There are a few places I'm being modest in terms of, transferability and chemical robustness. If you read our paper on this, you'll know that these are pretty much there, but there are a few things that we would like to, investigate further. And so I'm not going to say they're violated. Everything we've seen says that these are satisfied, but the verdict is still out. I'm not as confident as I am about the other. Certainly, all the mathematical properties are there. Most of the chemical properties are there, and the practicality is amazing. You can, it's a very simple equation. Not only can you run it very quickly on your laptop, you can write the code for it in, probably a day. I said I would say something about my path, and I stopped basically at some point. So there's a lot of other things that I have, if I go back to my original analogy, I've sort of been like a carpenter who's constantly hitting his thumb, with related to quantum information. Shubin has got me very interested in information theoretic descriptors, more for molecular property prediction and chemical insight. And recently we started thinking about information theory in the quantum optimal transfer context. And with that, I'm finished. I thank you all for your attention.
Professor Ayers, thank you very much for your presentation. So this last talk closes the session, and we will be back at 4 for the last session of the conference. Thank you.